Good evening and welcome to Physic for Sleep. Tonight we embark on an intellectual journey exploring the ultimate speed limit of the cosmos, the speed of light, and why it stands as an unbreakable barrier in our universe. Before we gently immerse ourselves in the profound implications of this cosmic constant, I would like to know where you are at this moment. Perhaps you are comfortably settled in your bed, gazing at the distant city lights through your window. Or perhaps you are wrapped in a soft blanket on a quiet porch. If these deep reflections help you relax and organize your thoughts before sleep, please support the channel with a like and subscribe so others can find their way here too. Now, just breathe. Allow your eyes to grow heavy, and let's begin. The journey into the profound nature of light begins with a number, a constant value that permeates the very fabric of our universe. This universal speed limit, approximately 299,792,458 meters per second in a vacuum, is not merely a fast speed. It is an absolute. It is a boundary that nothing in our cosmos possessing mass can ever reach or exceed. This isn't an arbitrary rule, but a deeply embedded property of space-time itself, a consequence of the intricate dance between energy, mass, and motion. To truly appreciate why this limit exists, we must delve into the insights gifted to us by Albert Einstein, particularly his theory of special relativity. Before Einstein, the ideas of space and time were largely considered separate and absolute, a universal stage upon which all events unfolded. But he revealed a more fluid, interconnected reality, where space and time are inextricably woven into a single fabric called space-time. And within this fabric, the speed of light, often denoted as c, holds a unique and unwavering position. Consider an object with mass, perhaps a spaceship, accelerating through the void. As it gathers speed, something remarkable begins to occur, something counterintuitive to our everyday experiences. Its mass starts to increase. This isn't a mere addition of material, but an intrinsic change in its inertial mass, its resistance to further acceleration. The faster an object moves, the more massive it becomes. This phenomenon is a direct consequence of the famous equation E=mc2, which eloquently demonstrates the equivalence of mass and energy. As an object accelerates, the energy imparted to it converts into an increase in its mass. Now, imagine our hypothetical spaceship approaching the speed of light. As it draws closer and closer to this cosmic barrier, its mass would grow exponentially. To reach the speed of light itself, the mass of the spaceship would become infinite. And to move an object with infinite mass would, in turn, require an infinite amount of energy. In a universe where resources are finite, even in principle, an infinite amount of energy is simply unobtainable. This elegant yet unyielding mathematical truth is why objects with mass are forever bound to speeds less than that of light. Light itself, composed of photons, has no rest mass, allowing it to travel at this ultimate velocity. It is not accelerating to the speed of light. It is born at it, and it ceases to exist when it is absorbed. This limit also profoundly influences our perception of time and space, revealing that they are not fixed, but relative. If you were aboard that accelerating spaceship approaching light speed, you would experience time passing differently than someone observing you from a stationary point on Earth. For you, inside the vessel, everything would feel normal. Your heart would beat at its usual rhythm. Your thoughts would flow at their accustomed pace. But to the observer on Earth, your clock would appear to tick more slowly. Your movements would seem sluggish, your very existence stretched in time. This is known as time dilation, a fundamental aspect of relativity, where time literally slows down for objects in motion relative to an observer. The closer you get to the speed of light, the more pronounced this effect becomes. Similarly, space itself would seem to compress. The length of your spaceship, as perceived by the stationary observer, would appear to shrink in the direction of its motion. This is length contraction. A journey that might seem incredibly long from an external perspective could appear shorter to someone traveling at relativistic speeds, as the very distances between celestial bodies would contract. Yet, for the traveler, the dimensions of their own vessel would remain unchanged. This suggests that our experience of space and time is intrinsically linked to our motion, painting a picture of a universe far more dynamic and interwoven than our classical intuitions suggest. The constancy of the speed of light also plays a crucial role in preserving causality, the fundamental principle that cause must precede effect. If it were possible to travel faster than light, one could, in theory, send information or even oneself back in time, creating paradoxes that would unravel the logical structure of our universe. Imagine receiving a message from your future self, warning you not to take a particular action, and then following that advice, thus preventing the very event that prompted the warning. Such scenarios violate causality, and the speed of light limit acts as a cosmic guardian, ensuring that the flow of cause and effect remains consistent and orderly throughout space-time. It ensures that the sequence of events, the very narrative of existence, unfolds in a coherent and predictable manner, preventing a chaotic tangle of possibilities. So, when we contemplate the speed of light, we are not merely considering a numerical value, but a profound statement about the nature of reality itself. It is a constant that defines the very architecture of space-time, dictating how mass and energy behave, how time flows, and how distances are perceived. It is a gentle reminder that our universe operates under elegant, unyielding principles, where movement is not just about changing position, but about interacting with the deep structure of the cosmos. As we drift towards sleep, let us carry this thought, that the speed of light, while an insurmountable barrier for physical travel, is also a window into the universe's most fundamental truths. A quiet hum in the background of existence, ensuring that everything remains beautifully, profoundly in its place. The preservation of causality, a silent guardian of our universe's logical flow, gently guides our thoughts toward the practical dimensions of this cosmic speed limit. For us, as beings rooted in space and time, the speed of light presents a profound challenge to our aspirations of traversing the vast interstellar ocean. Consider the nearest star system to our own, Alpha Centauri, residing at a distance of approximately 4.37 light-years. This means that even if we could develop a spacecraft capable of traveling at nearly the speed of light, a one-way journey would still take over 4 years from the perspective of an observer on Earth. For the intrepid traveler aboard such a vessel, however, the experience would be different, a testament to the marvel of time dilation. As discussed, time would slow down for them. A journey to Alpha Centauri might feel like only a few months, or even weeks, depending on how close to the speed of light they could truly approach. Yet, upon their return to Earth, if such a return were even possible, they would find that many decades, perhaps even centuries, had passed for their loved ones and for humanity. This is the essence of the famous twin paradox, not a paradox in the sense of a logical contradiction, but a deep truth about the relativity of time. It illustrates that travel to distant stars, while physically conceivable in terms of the traveler's subjective experience, becomes a journey through time as much as through space for those left behind. It transforms interstellar voyaging into a one-way passage for the individual, a profound commitment to a future utterly disconnected from their point of origin. This cosmic constraint subtly reminds us of the precious singular nature of our own temporal thread within the grand tapestry of existence. This interplay of space and time is beautifully encapsulated by the concept of the light cone. Imagine a three-dimensional graph where 2 axes represent space and the third represents time. From any given event, light expands outward in all directions, forming a cone. Everything within your past light cone represents all the events in space-time that could have causally influenced you, as light or information from them has had time to reach you. Conversely, everything within your future light cone represents all the events you can possibly influence. Nothing outside your light cone, neither in the past nor the future, can affect you or be affected by you. The edges of this cone are defined by the path of light itself, the fastest possible connection across the cosmos. It's a serene, geometric representation of our causal universe, showing us that while the universe is vast, our immediate causal reach is intimately bound by the speed of light. It defines our sphere of influence and experience, a gentle reminder of our place within the universal flow. Perhaps the most astonishing implication of the speed of light is its effect on light itself. For a photon, a particle of light, time does not flow, and distance does not exist. From the moment a photon is emitted, say, from the surface of a distant star, to the moment it is absorbed by your eye, it experiences zero time. Its journey across billions of light years is, from its own perspective, instantaneous. It is born and absorbed in the same singular moment. This is not a metaphor, it is a direct consequence of the laws of special relativity. If an object were to reach the speed of light, its proper time, the time measured by a clock moving with it, would halt. Its length in the direction of motion would contract to zero. This profound insight means that photons are, in a sense, outside of our familiar space-time. They are pure carriers of information and energy, traversing the cosmos without experiencing the very dimensions they help define for us. They are timeless messengers, connecting the most distant reaches of the universe in a way we can only conceptually grasp. This absolute speed limit also has far-reaching implications for communication across the cosmos. Any message, whether a radio signal, a laser pulse, or even a thought experiment, can travel no faster than light. If we were to send a greeting to a potential civilization on a planet orbiting Alpha Centauri, our message would take over 4 years to arrive. And if they were to respond immediately, their reply would take another 4 years to reach us. A simple hello and how are you would span nearly a decade. This inherent delay shapes our understanding of potential interstellar communication, emphasizing the profound silence and isolation that distance imposes. It fosters a contemplative patience, a deep appreciation for the vastness that separates potential minds across the cosmic ocean. Modern scientific endeavors, such as the search for extraterrestrial intelligence, are deeply informed by this constraint, reminding us that any dialogue with a distant intelligence would be a conversation stretched across immense spans of time. It is also vital to remember the universality of this constant. The speed of light in a vacuum is invariant. It is measured to be the same by all inertial observers, regardless of their relative motion or the motion of the light source. This was a revolutionary concept introduced by Einstein, departing from classical physics where speeds are additive. Whether you are standing still, moving towards a light source, or moving away from it, you will always measure the speed of light to be precisely. This unwavering constancy is not merely a peculiar fact, it is a fundamental pillar of our physical reality, an anchor in the ever-shifting sea of relative motion. It ensures a consistent framework for all physical laws, making it truly a universal constant, a steady pulse at the heart of the cosmos. As we reflect on these concepts, we find that the speed of light is far more than just a velocity. It is a defining characteristic of our universe, a constant that weaves together space, time, mass, and energy into a coherent, interconnected whole. It sets the rhythm of cosmic interactions, shapes the possibilities of travel and communication, and fundamentally dictates what we can observe and what can observe us. It is a quiet, elegant boundary that, rather than limiting our wonder, deepens our understanding of the delicate balance and intricate laws that govern our existence. And so, as these thoughts settle, we may find a tranquil reassurance in the universe's steadfast principles, knowing that even in the boundless expanse, there are fundamental rules that hold true, providing a stable backdrop for our brief, conscious flicker within its grandeur. The unwavering nature of the speed of light as a cosmic constant, might lead one to ponder if there are any subtle exceptions or ingenious pathways that could, in essence, circumvent this fundamental barrier. While direct travel at or beyond the speed of light for objects with mass remains impossible, theoretical physics offers us glimpses into fascinating, albeit highly speculative, methods of traversing vast cosmic distances without violating Einstein's principles locally. These concepts are not about breaking the speed limit, but rather bending the very road itself. One such captivating idea is the Alcubierre warp drive, proposed by physicist Miguel Alcubierre in the year 1994. This concept, rooted firmly in the equations of general relativity, does not suggest that a spacecraft would move faster than light through space. Instead, it posits a way to manipulate space-time itself. Imagine a bubble of space-time, a localized distortion that would contract space in front of the vessel and expand space behind it. Within this warp bubble, the spacecraft itself would remain stationary relative to its immediate surroundings, moving at ordinary sublight speeds. However, the bubble, carrying the ship within it, could effectively traverse vast distances at speeds that appear superluminal to an outside observer. It's akin to standing on a moving walkway. You are walking at a normal pace, but the walkway itself is carrying you much faster. This theoretical elegance avoids the problem of infinite mass and energy because the ship itself isn't accelerating through space to light speed. Yet the energy requirements for such a feat are truly astronomical, far beyond our current technological capabilities, often requiring quantities of exotic matter with negative energy density. It remains a beautiful, tranquil thought experiment, a testament to the flexibility of space-time, but one confined to the realm of deep theoretical exploration. For now. Another captivating idea that frequently surfaces in discussions of cosmic travel is the concept of wormholes. These are not methods of exceeding the speed of light, but rather hypothetical shortcuts through the fabric of space-time, connecting two distant points instantaneously, or nearly so. Imagine folding a piece of paper and piercing it with a pencil. The pencil creates a direct path between 2 points that were far apart on the two-dimensional surface. In a similar vein, a wormhole would be a tunnel through the higher dimensions of space-time, linking two disparate regions of our three-dimensional universe. Traveling through a wormhole would not mean moving faster than light, but simply traversing a much shorter path. The journey within the wormhole itself would still be at sublight speeds, yet the overall effect would be a near instantaneous leap across light years. The existence of wormholes, however, remains purely theoretical. If they do exist, their stability would likely require the presence of exotic matter with negative energy, similar to warp drives, to prevent them from collapsing the moment something attempts to pass through. They are ethereal bridges in the cosmic imagination, offering a serene, almost dreamlike passage across the universe, yet their construction and stability present immense, currently insurmountable challenges. Then there is the intriguing phenomenon of quantum entanglement, which often leads to misconceptions regarding faster-than-light communication. When two particles become entangled, they become intrinsically linked, sharing a common fate regardless of the distance separating them. If you measure a property of one entangled particle, such as its spin, the corresponding property of the other particle is instantaneously determined, even if they are light years apart. This seems to suggest information transfer at superluminal speeds. However, a crucial point here is that no information, in a meaningful, controllable sense, can be transmitted faster than light, using entanglement. While the states are correlated instantaneously, there is no way for one observer to manipulate their entangled particle to send a specific message to another observer faster than light. You cannot choose the outcome of your measurement to encode a message. The outcomes are inherently random, only becoming known upon measurement, thus preserving the universal speed limit for communication. Entanglement, therefore, is not a loophole for superluminal messaging, but rather a profound illustration of the non-local nature of quantum reality, a silent, interconnected dance of particles across the cosmos that quietly respects the rules of causality. Beyond these theoretical constructs, our observations of the universe itself present phenomena that, at first glance, might seem to defy the speed of light. Consider the expansion of the universe. Distant galaxies are observed to be receding from us and from each other at speeds that appear to exceed the speed of light. However, this is not a violation of Einstein's principles. These galaxies are not moving through space at superluminal velocities. Rather, the space between them is expanding, carrying them apart. Imagine dots on the surface of an inflating balloon. The dots themselves are stationary on the surface, but the distance between them increases as the balloon expands. Similarly, the fabric of space-time itself is stretching, causing galaxies to drift further apart. This cosmic expansion, driven by dark energy, is a large-scale phenomenon that does not imply objects are breaking the local speed limit. It simply means that the vastness of the universe is growing, defining a cosmic horizon beyond which light from certain regions will never reach us, regardless of how long we wait. This grand, gentle stretching of the cosmos is a reminder of the dynamic, evolving nature of our universe, a silent, ceaseless unfolding that shapes our observable reality. Finally, to deeply understand why mass prevents something from reaching the speed of light, we can touch upon the role of the Higgs field. This pervasive quantum field, theoretically predicted by Peter Higgs and others, gives fundamental particles their mass. Particles interact with the Higgs field, and this interaction imparts inertia or mass to them. The stronger the interaction, the more massive the particle. Photons, the particles of light, do not interact with the Higgs field and thus remain massless. This is precisely why they can travel at the speed of light. Any particle that interacts with the Higgs field, acquiring even a minuscule amount of mass, becomes inherently bound by the speed limit, needing infinite energy to reach c. The Higgs field, therefore, is the subtle, invisible hand that explains a fundamental part of the universe's speed constraint, a deep, quiet mechanism underlying the very nature of existence. It is a profound, elegant explanation for why some things are destined to travel at light speed and why others are forever held just below that ultimate velocity, each playing their role in the cosmic ballet. These concepts, from the bending of space-time to the whispers of quantum correlation and the deep origins of mass, illustrate that the speed of light is not merely a number, but a profoundly integrated element of the universe's architecture. It shapes the very possibilities of reality, gently guiding the flow of events and the nature of all interactions. It is a constant that, even when approached through the lens of theoretical circumvention, only further reinforces its fundamental role, creating a harmonious and logically coherent cosmos in which we, as conscious observers, quietly exist. The profound implications of light's ultimate speed extend far beyond the mechanics of individual particles or hypothetical spacecraft. They fundamentally define our very perception of the universe. This cosmic speed limit, you see, is not just about how fast things can travel, but about how much of reality we can ever hope to observe. Because light, even at its astonishing speed, takes time to traverse the immense distances of space. Every photon that reaches our eyes from a distant star or galaxy carries with it a story of the past. When you gaze up at the night sky, you're essentially looking into a cosmic archive, witnessing events that unfolded millions, even billions, of years ago. The light from the Andromeda Galaxy, our nearest large galactic neighbor, takes approximately 2.5 million years to reach us. What we see tonight is not Andromeda as it is now, but as it was 2.5 million years ago, a snapshot from a distant epoch. This temporal delay means that there's a limit to how far back in time we can see, defining what we call the observable universe. Beyond a certain boundary, roughly 46.5 billion light-years in radius, light simply hasn't had enough time since the Big Bang to reach us. It's a vast horizon of unseen history, a quiet reminder that the universe extends far beyond our current observational reach, unfolding its grand narrative in a silent, patient manner. This concept truly brings home the idea that our personal now is a local phenomenon. There is no universal present moment shared across the entire cosmos. Imagine two distant observers, each looking at the same celestial event. Because of the vast distances and the finite speed of light, they will witness that event at different points in their own local timelines. What is past for one might still be the future for another, depending on their relative positions and motions. This isn't a trick of perception, but a fundamental truth of space-time, a beautiful, intricate dance of relative realities. It invites a contemplative quietude, a recognition that our own existence is a unique thread in a tapestry of countless unfolding moments, each observer experiencing their own sliver of cosmic time. And when we consider this, the enormity of what we can see, the ancient light that has traveled so far to reach us, becomes even more precious, a testament to the universe's enduring story. Now, while we speak of the speed of light in a vacuum as an absolute constant, it is important to clarify that light can and does travel slower when passing through a medium, such as water, glass, or even Earth's atmosphere. This apparent slowing down, however, is not a violation of the universal speed limit of c. The speed of light in a vacuum remains constant. What happens when light enters a medium is that its photons are constantly absorbed and re-emitted by the electrons in the atoms of that material. Each individual photon still travels at c between these interactions, but the cumulative effect of these delays, these tiny moments of absorption and re-emission, causes the overall or effective speed of the light wave to decrease. It's like a runner on a crowded street. They might sprint at their top speed between obstacles, but the constant stopping and starting to navigate the crowd makes their average speed much lower. This gentle interaction between light and matter is what gives rise to phenomena like refraction, where light bends as it passes from one medium to another, creating the shimmering effects we see through water or the sparkle of a prism. It is a nuanced dance, a quiet interplay that enriches our visual world without ever compromising the fundamental, unyielding speed of light in the emptiness of space. This distinction leads us to another fascinating, almost poetic phenomenon: Cherenkov radiation. This occurs when a charged particle, such as an electron, travels through a transparent medium like water at a speed greater than the speed of light in that particular medium. It's not faster than c, the universal speed limit in a vacuum, but faster than light's effective speed in that specific material. When this happens, the particle creates a kind of light boom, analogous to a sonic boom produced by an aircraft, breaking the sound barrier. The radiation emitted is often a beautiful ethereal blue glow, visible around nuclear reactors or in special scientific experiments. It's a serene, silent cascade of light, a gentle whisper of energy released when a particle briefly outpaces the local speed of photons. This phenomenon beautifully reinforces the absolute nature of c in the vacuum, while also illustrating the rich and varied ways light interacts with the world around us. A subtle reminder that even within strict physical laws, there are moments of unexpected beauty and subtle defiance. The very structure of space-time is also intrinsically tied to the speed of light through the concept of the space-time interval. While observers in different frames of reference will measure different distances and different durations of time between two events, a remarkable truth emerges. The space-time interval itself remains invariant. This interval, a combination of space and time measurements, is an absolute quantity, agreed upon by all observers. It's like the diagonal distance across a room. Even if two people measure the length and width differently due to their perspective, the overall diagonal distance remains the same. The speed of light acts as the conversion factor between units of space and units of time in this four-dimensional geometry. It's the intrinsic constant that links all measurements in space-time, providing a fundamental bedrock of reality that transcends individual perceptions. This deep mathematical elegance underpins our universe, offering a sense of profound order and consistency. a quiet reassurance that beneath the apparent relativity of our experiences, there lies an unwavering, interconnected truth. In essence, barrier, but a foundational principle that sculpts the very universe we inhabit. It dictates the rhythm of cosmic communication, shapes the horizons of our knowledge, and underpins the intricate relationships between mass, energy, space, and time. It is a constant that, in its quiet omnipresence, ensures the coherence and logical unfolding of all cosmic events. As we contemplate this ultimate speed, we might find a deep sense of calm, understanding that the universe in its vastness and complexity operates with an elegant simplicity, a set of unyielding rules that allow for the beautiful, intricate dance of existence. It is a constant that, rather than limiting our dreams of interstellar travel, deepens our appreciation for the profound and intricate laws that govern every moment of our being. The quiet elegance of the speed of light, defining the very fabric of our reality, is not merely a theoretical construct. It is a constant, rigorously tested and confirmed by countless observations and experiments throughout history. From the earliest inquisitive minds to the most sophisticated modern laboratories, humanity has sought to grasp the elusive nature of light, slowly uncovering its profound role as the universe's ultimate speed. Centuries ago, the prevailing wisdom held that light traveled instantaneously. It seemed to appear everywhere at once, an immediate presence. But even then, some thinkers dared to question this intuition. Galileo Galilei, in the early 1600s, attempted to measure its speed with lanterns on distant hills, though his methods were too crude to capture its immense velocity. It was the Danish astronomer Ole Romer in the late 1670s who first provided compelling evidence that light has a finite speed. By observing the irregular eclipses of Jupiter's moon Io, he noticed discrepancies that could only be explained if light took time to travel from Jupiter to Earth, depending on the planet's varying distances. His early estimate, though not entirely accurate by modern standards, was a monumental step, a quiet whisper that the universe's swift messenger was not infinitely fast. Later, in the mid-1800s, French physicists Hippolyte Fizeau and Léon Foucault, using ingenious laboratory setups involving rotating mirrors and toothed wheels, provided increasingly precise measurements, bringing the cosmic constant ever closer to its true value. These early efforts, a testament to human curiosity and ingenuity, laid the groundwork for a deeper understanding, transforming light from a mystical phenomenon into a measurable physical entity. The true theoretical understanding of light speed, however, emerged from the brilliant work of James Clerk Maxwell in the mid-1800s. He unified the seemingly disparate forces of electricity and magnetism into a single, elegant framework: Maxwell's equations. These four fundamental equations described how electric and magnetic fields generate and interact with each other. And within these equations, a profound prediction lay hidden: that disturbances in these fields propagate as waves, electromagnetic waves, and they would travel at a very specific, calculable speed. When Maxwell performed the calculations using known electrical and magnetic constants, the speed he derived was astonishingly close to the experimentally measured speed of light. This was not a coincidence. It revealed that light itself is an electromagnetic wave, a ripple in the invisible fields that permeate space. This realization was a quiet revolution, unveiling light, not as something that travels through a medium, but as a self-propagating vibration of fields, inherently possessing its constant velocity. It was a moment of profound unification, painting a picture of a universe where light is an intrinsic part of its electromagnetic tapestry. The advent of particle accelerators in the 20th century provided further highly rigorous confirmation of the speed of light limit and the relativistic effects it entails. In these colossal machines, particles such as protons and electrons are accelerated to speeds incredibly close to c, often reaching 99.9999% of light speed. Scientists observe directly how their mass increases dramatically, precisely as predicted by Einstein's equations. The particles become so heavy that further acceleration requires increasingly enormous amounts of energy, making it practically impossible to reach the absolute limit. Furthermore, the lifetimes of unstable particles, when accelerated to these relativistic speeds, are observed to stretch or dilate exactly as special relativity predicts. Muons, for instance, are subatomic particles with a very short natural lifespan. When created in our atmosphere by cosmic rays, they travel at near light speed. If time did not dilate for them, they would never reach the Earth's surface before decaying. Yet they do. Their extended lifetimes, precisely matching relativistic calculations, serve as a gentle, undeniable confirmation of time dilation. These experiments are not merely academic exercises. They are profound affirmations of the universe's fundamental rules, a continuous quiet whisper from the heart of matter itself. The constant speed of light, this cosmic bedrock, is not just a theoretical curiosity. It underpins many of the technologies that shape our modern world. Consider the Global Positioning System, or GPS. The satellites orbiting Earth transmit signals at the speed of light. For GPS to function with the incredible accuracy we rely on, providing precise location data, it must account for relativistic effects. The clocks on these satellites, moving rapidly relative to Earth and experiencing slightly weaker gravity, tick at a different rate than clocks on the ground. Without constant corrections based on both special and general relativity, the timing signals would drift, accumulating errors of many kilometers per day. Your car navigation, your smartphone's location services, all quietly depend on Einstein's profound insights into the nature of light and space-time. It's a subtle, invisible influence, a testament to how deeply the universe's fundamental laws are woven into the fabric of our daily lives, a serene harmony between cosmic constants and human innovation. Even our exploration of the cosmos, looking out at the distant galaxies through powerful telescopes, is fundamentally governed by this speed limit. Every image we capture, every spectrum we analyze, is a transmission from the past, limited by the time light has taken to reach us. This means that when astronomers study the most distant objects, they are essentially looking at the universe as it was in its infancy, billions of years ago. The speed of light acts as a cosmic time machine, allowing us to reconstruct the universe's history, piece by gentle piece. It is a profound gift, this finite speed, offering us a window into the origins of stars and galaxies, a chance to witness the universe's grand evolution. It teaches us patience, reminding us that the vastness of space is also a vastness of time, and that understanding the cosmos requires a quiet, reflective contemplation of its ancient light. Ultimately, the speed of light is more than just a measurement. It is a fundamental constant that defines the very essence of our universe. It dictates the interaction between mass and energy, shapes the flow of time and the perception of space, underpins our technology, and limits our observational reach. It is a constant that, in its unwavering nature, provides a stable, predictable framework for all physical phenomena. Rather than being a frustrating barrier, it is a source of profound wonder, revealing a universe of elegant laws and interconnected truths, a serene stage upon which the cosmic drama quietly unfolds. And in understanding this, we may find a deeper appreciation for the delicate balance that allows for the existence of everything, including ourselves, a brief conscious flicker within its boundless and beautifully constrained expanse. Implications of light's finite speed extend profoundly to our understanding of the universe's vastness and the limits of our knowledge. As we peer into the depths of the cosmos, every photon that touches our telescopes carries with it the story of a distant past. The light from the most remote galaxies has traveled for billions of years to reach us, meaning we are witnessing these celestial structures not as they are now, but as they were eons ago. This inherent delay creates what is known as the cosmic horizon, a boundary of information, a gentle veil beyond which the universe's current state remains a mystery to our instruments. It is not a physical wall, but a limit to what signals, what stories, have had enough time to arrive at our cosmic doorstep. This quiet truth means that the universe we observe is, in many ways, an ancient portrait, a collection of snapshots from different eras, arranged according to the travel time of light. We are, in a sense, each at the center of our own observable universe, a unique bubble of light-reachable reality, forever limited by the speed at which information can travel. This realization fosters a deep sense of humility and wonder, as it reminds us that much of the universe's grandeur, its ongoing present, unfolds beyond our capacity to perceive, a silent, continuous unfolding in the cosmic dark. This limitation also brings with it a profound sense of cosmic isolation. Because no information can travel faster than light, any civilizations in galaxies beyond our light cone, or even within it, but too far for two-way communication, are forever separated from us in a practical sense. A message sent across billions of light years might arrive long after the sender, or even their entire civilization, has ceased to exist. This vast cosmic silence, often referred to as the Fermi paradox in some contexts, is a direct consequence of the speed of light. It suggests that while the universe may be teeming with life, the sheer distances and the unyielding speed limit make meaningful real-time interaction an impossibility. This understanding can evoke our own brief flicker of consciousness, is a unique and precious phenomenon, unfolding within a vast, largely unreachable cosmic tapestry. It emphasizes the profound self-reliance of each pocket of life, each a solitary island of awareness in an ocean of light-speed-bound silence. The concept of a universal now is further dissolved by this understanding. Your now is a unique point in space-time, a personal slice of reality that shifts with your motion and gravitational context. For an observer on a distant exoplanet, what is happening for you right now might be their distant past or their far future. There is no absolute universal moment of now that binds all observers across the cosmos. This radical departure from our everyday intuition, first unveiled by Einstein, means that every individual, every planet, every star exists within its own local timeline, a unique rhythm dictated by the geometry of space-time around it. It's a gentle reminder of the subjective nature of our temporal experience, a tranquil thought that each of us is living our own unique sequence of moments, interwoven yet distinct within the grand four-dimensional block of space-time, while the speed of light stands as an unyielding constant for anything with mass. The human mind continues its serene quest for understanding, always probing the edges of the known. Theoretical physicists continue to explore concepts that, while not breaking the speed of light, might offer new perspectives on its nature or the universe's structure. Ideas such as tachyons, hypothetical particles that always travel faster than light, have been proposed. However, such particles would face their own set of profound challenges, including violating causality, making their existence highly problematic for our current understanding of physics. The exploration of such concepts is not an attempt to defy the fundamental limit, but rather a testament to the ongoing human drive to understand the universe in its entirety, to push the boundaries of what is conceivable within the elegant framework of physical laws. This quiet, persistent inquiry, even into the realm of the currently impossible, is a deep part of our scientific journey, a continuous meditative search for deeper truths. Ultimately, this cosmic limit, then, becomes a frame for our own fleeting existence, a gentle reminder that our conscious experience is a unique unfolding within an ancient, vast, and beautifully constrained cosmos. It is a boundary that, rather than diminishing our sense of possibility, deepens our appreciation for the intricate and harmonious speed of light, is a profound and beautiful truth. A constant that quietly ensures the coherence of the universe, allowing for the gentle dance of stars, galaxies, and life itself to unfold within its elegant bounds. It is a source of tranquil wonder, inviting us to reflect on our place within this grand, illuminated story. and our brief yet significant role in its ongoing narrative. As the echoes of these profound concepts gently recede, we are left with a tranquil understanding. Cosmic barrier, but a fundamental truth, a silent architect of our universe. It dictates the rhythm of space-time, shapes the very fabric of reality, and defines the horizons of our perception. This immutable constant ensures that the cosmos unfolds with a majestic coherence, a predictable dance of cause and effect. It is a source of deep wonder, reminding us that even within its boundless expanse, there are elegant, unwavering laws that govern all existence, from the smallest photon to the grandest galaxy. And as we drift into the quietude of the night, let us carry this serene thought, that we are all part of this astonishing, light-bound universe, our brief lives illuminated by the ancient, unwavering glow of its most fundamental constant. May these deep thoughts about the absolute limit of the universe carry you into a world of tranquil sleep. Remember that the universe is amazing and you are a part of it. Fall asleep with this feeling of serenity and endless knowledge. Good night. We begin by considering the sheer scale of the distances involved, even within our own cosmic neighborhood. Our solar system, vast as it seems to us, is a mere speck when measured against the interstellar void. To truly appreciate this scale, imagine our fastest spacecraft, like the Voyager probes, which have now passed beyond the heliopause, the boundary where the sun's protective influence wanes. These intrepid explorers have been traveling for over 45 years, moving at speeds of tens of thousands of kilometers per hour. Yet, even at these incredible velocities, they are still barely crawling in cosmic terms. The nearest star system to our own, Alpha Centauri, is approximately 4.37 light-years away. To grasp what a light-year truly signifies, consider this. Light, the fastest thing in our universe, travels at nearly 300,000 kilometers per second. In 1 year, it covers a distance so immense that it is almost beyond human comprehension, roughly 9.46 trillion kilometers. So, Alpha Centauri is not just a few million kilometers distant, it is tens of trillions of kilometers from our home. If one of our Voyager probes were directed towards Alpha Centauri today, its journey would take roughly 73,000 years. 73 millennia. That is a span of time longer than recorded human history, longer than the entire existence of our modern civilization. Imagine launching a spacecraft today, knowing that its destination would not be reached until our species might have profoundly changed, or perhaps even vanished. The individuals who launched it, their great-grandchildren, and countless generations after them would all live and die before the probe even caught a glimpse of its target star. This vast temporal gulf is the first and perhaps most fundamental hurdle to any realistic form of interstellar travel. The challenge is not merely technological, but deeply existential. How do we design a mission that outlasts empires, that spans the entire known history of humanity? It forces us to confront the inherent brevity of individual human lives against the backdrop of cosmic timescales. Even if we could accelerate a craft to 1% of the speed of light, which is far beyond our current technological capabilities, the journey to Alpha Centauri would still take over 400 years. This is a voyage that would inherently require generations to complete, a multi-generational ship where the descendants of the original crew would be the ones to finally arrive at the new star. This concept of a generation ship introduces complex sociological and biological problems that are as daunting as the engineering feats required. Consider the profound human element of such an endeavor. A crew embarking on such a voyage would need to be entirely self-sufficient for centuries, living in a closed ecosystem, meticulously maintaining a delicate balance of resources and preserving knowledge and culture across many births and deaths within the confines of their vessel. The psychological toll of living in an enclosed environment, never seeing a true sky, knowing that your purpose is merely to continue a journey your ancestors began and your descendants will eventually complete, is immense. How do you maintain purpose, avoid despair, and ensure the genetic and cultural health of a population confined to a metallic shell hurtling through the void for hundreds of years? These are not questions of propulsion or navigation, but of what it means to be human in the most extreme isolation imaginable, a profound test of our collective resilience and adaptability. Scientists and engineers have long dreamt of faster-than-light travel, often depicted in science fiction as a convenient solution to these immense distances. Concepts like warp drives or traversable wormholes offer tantalizing possibilities, but they remain firmly in the realm of theoretical physics or even pure speculation at our current understanding. The fundamental physical challenge is Einstein's theory of special relativity, which dictates that nothing with mass can accelerate to the speed of light, let alone surpass it. As an object approaches light speed, its mass effectively increases towards infinity, requiring an infinite amount of energy to accelerate further. This cosmic speed limit is not a technological barrier we can simply overcome with better engines. It is a fundamental property of space-time itself, a law woven into the very fabric of the universe. So, while the dream of traversing the stars quickly persists, the reality of our current understanding of physics places a hard limit on our interstellar aspirations. To leave our solar system and reach another star system within a single human lifespan would require breakthroughs that fundamentally redefine our understanding of energy, mass, and the very geometry of space-time. Until then, any interstellar voyage remains a monumental undertaking, a testament to enduring patience, a slow, relentless march of generations, and a profound meditation on our fleeting existence within the boundless cosmos. It reminds us that even the most ambitious dreams must contend with the universe's immutable laws, prompting us to consider what true exploration might entail beyond mere speed. Beyond the sheer immensity of distance and the relentless march of time, interstellar travel confronts us with a formidable array of physical and engineering challenges, beginning with the very act of propulsion. To accelerate a spacecraft to even a fraction of light speed, and then, crucially, to decelerate it upon arrival, demands quantities of energy that defy our current imagination and technological grasp. The classic rocket equation, while elegant in its simplicity, reveals a stark truth. To achieve higher velocities, an exponentially greater amount of fuel is required. For conventional chemical rockets, this quickly becomes impractical. The mass of the fuel needed to accelerate the fuel itself becomes overwhelming. This fundamental limitation has led scientists to explore more exotic forms of propulsion. One such concept is nuclear pulse propulsion, famously explored in the Orion project of the mid-20th century. The idea was to propel a spacecraft by detonating a series of nuclear bombs behind it, using the explosive force to push a massive pusher plate. While theoretically capable of reaching perhaps 10% of light speed, the engineering hurdles, not least the sheer scale of the detonations and the radiation they would produce, made it a project far ahead of its time and ethically controversial in an era of nuclear proliferation concerns. It remains a powerful illustration of the extreme measures required to move substantial mass across astronomical distances. Looking further into the future, fusion rockets, harnessing the power of controlled nuclear fusion, offer a more elegant solution. By fusing light elements like deuterium and tritium, these engines could produce enormous amounts of energy with relatively small fuel masses, offering a more efficient exhaust velocity than chemical or even fission rockets. However, controlled fusion on Earth is still a grand scientific challenge, something we are only now beginning to achieve for very short durations in laboratories. To build a fusion reactor compact enough, robust enough, and reliable enough to power an interstellar vessel for centuries remains a monumental engineering feat, a distant horizon on our technological roadmap. Even more ambitious is the concept of antimatter propulsion. When matter and antimatter meet, they annihilate, converting their entire mass into energy with 100% efficiency, according to Einstein's famous equation, E equals mc squared. This is the most energy-dense reaction known to physics, making antimatter rockets theoretically capable of approaching a significant fraction of light speed. Imagine a starship powered by mere grams of antimatter, offering unparalleled thrust. Yet the challenges are staggering. Antimatter is incredibly difficult and energy-intensive to produce, requiring vast particle accelerators, and even then, only in minuscule quantities. Furthermore, storing antimatter safely for decades or centuries on an interstellar journey, preventing it from touching ordinary matter and annihilating prematurely, is a problem for which we currently have no practical solution. It is a dream of immense power tethered to profound, unresolved difficulties. Then there are concepts that require no onboard fuel at all, such as solar sails or laser sails. A solar sail, much like a ship's sail, uses the pressure of photons from a star to slowly accelerate a spacecraft. While effective for small probes within a solar system, the light pressure diminishes rapidly with distance, making sustained acceleration for interstellar travel incredibly slow. Laser sails, on the other hand, propose using powerful ground-based or orbital lasers to push a lightweight reflective sail to much higher speeds. Projects like Breakthrough Starshot envision sending tiny gram-scale probes to Alpha Centauri at 20% of light speed within a few decades using this method. However, this still requires laser arrays of unprecedented power, capable of focusing a beam across astronomical distances with pinpoint accuracy. And the challenge of decelerating the probe once it reaches its destination remains. The target star system would have no equivalent laser array to slow the craft down, leaving it to zip past its destination at extreme speeds, offering only a fleeting glimpse. Beyond propulsion, the very environment of interstellar space is far from empty and benign. It is a vacuum, yes, but a vacuum teeming with hazards. The most insidious of these is cosmic radiation. Our solar system is protected by the Sun's magnetic field and the Earth's atmosphere, but outside this bubble, spacecraft and biological systems are exposed to a relentless barrage of high-energy particles. Galactic cosmic rays originating from supernovae and other violent astrophysical events across the galaxy can penetrate spacecraft hulls and human tissue, causing cellular damage, increasing cancer risk, and potentially leading to cognitive impairment over long exposures. Shielding against this type of radiation is incredibly difficult, as very thick layers of material would be required, adding prohibitive mass to any vessel. For human crews, this means a constant, invisible threat, a slow erosion of health over decades. Furthermore, even seemingly empty space is not truly empty. It contains microscopic dust grains and micrometeoroids. At interstellar velocities, even a speck of dust, no larger than a grain of sand, could strike a spacecraft with the kinetic energy of a rifle bullet, potentially causing catastrophic damage to sensitive equipment or even breaching the hull. The probability of such impacts increases over vast distances and prolonged travel times. Detecting and avoiding these minute projectiles in the immense void, especially at relativistic speeds, presents a profound challenge to navigation and spacecraft design. So, when we consider leaving our solar system, we are not merely contemplating a journey, but a profound redefinition of human endurance and ingenuity. It demands not only revolutionary physics and engineering, but also a deep introspection into our species' capacity for sustained collective effort, for overcoming the inherent fragility of life in a universe that is both magnificent and utterly indifferent to our aspirations. It is a test of our will to persist, to build a future beyond our planetary cradle, no matter how distant or dangerous that future may be. Having contemplated the immense distances and the fundamental limits of speed, our journey of thought now turns to the destination itself, the elusive exoplanets that might one day offer a new home. The discovery of thousands of planets beyond our solar system has ignited a quiet hope, a vision of humanity finding its place among the stars. Yet each new discovery also underscores a profound challenge, identifying a world truly capable of sustaining complex life, or even simple human colonization, is far more intricate than merely locating a planet within a star's habitable zone. This Goldilocks zone merely suggests the potential for liquid water on a planet's surface, but a truly hospitable environment requires a delicate ballet of countless other factors. Imagine a world tidally locked to its star, one side perpetually bathed in searing heat, the other frozen in eternal darkness, with only a narrow twilight band offering temperate conditions. Or consider a planet orbiting a volatile red dwarf star, prone to frequent powerful flares that could strip away an atmosphere or sterilize a surface. These are not merely hypothetical scenarios, they represent realities for many of the exoplanets we have detected so far. Furthermore, a planet needs a robust magnetic field to deflect harmful stellar radiation, a stable atmosphere with the right chemical composition, and a geological activity to recycle essential nutrients. Even the presence of a large moon can be crucial, stabilizing a planet's axial tilt and preventing extreme climate swings. Each of these necessary conditions acts as a filter, narrowing the seemingly endless possibilities down to a precious few. And for most distant worlds, we currently lack the means to ascertain these intricate details. Should we overcome the immense distances and find such a celestial haven, the challenge of communication across the void would become a constant, quiet presence. Even at the speed of light, signals to Alpha Centauri would take over 4 years to reach their destination, and another 4 years for a reply to return. For a mission to a star system 20 light-years away, a simple question and answer would span 40 years, a significant portion of a human lifetime. This immense delay fundamentally alters the nature of control and connection. There could be no real-time command from Earth, no immediate response to unforeseen crises. The interstellar vessel would need to be entirely autonomous, its crew empowered to make life or death decisions without guidance, living in a permanent state of self-reliance, detached from the originating authority. This profound temporal separation also deepens the existential isolation for the crew. Messages from Earth would arrive as echoes from the past, news of events that transpired years or decades ago, a bittersweet reminder of a home that is increasingly distant, both physically and culturally. The psychological impact of such a disconnect is difficult to overstate. For generations born and raised aboard a starship, Earth would become a mythical ancestral land, a concept more than a tangible place. Their culture, their very identity, would necessarily evolve within the confines of their vessel, forging new traditions, new values, perhaps even new languages, distinct from the world they left behind. This raises a quiet, contemplative question. At what point does a journey of exploration become the founding of a new, entirely separate civilization? The very structure of a multi-generational mission also presents unique biological and sociological challenges. A small founding population, even with careful genetic screening, would face the risks of genetic drift and reduced genetic diversity over centuries. This could make them more susceptible to unforeseen diseases or environmental changes within their enclosed habitat. Beyond biology, the sociological dynamics of a closed community, confined to a vessel for many lifetimes, would be a constant, delicate balancing act. How would leadership be established and maintained? How would conflicts be resolved when there is no outside to appeal to, no escape? The purpose of the mission, initially so clear and compelling, could become diluted or reinterpreted by successive generations, potentially leading to a loss of the original drive or even internal schisms. Maintaining a cohesive, purposeful society under such extreme, prolonged isolation would be a triumph of human organization and psychology, a truly profound experiment in societal endurance. The material needs of such a long voyage are equally demanding. A generation ship would need to be a perfectly self-sustaining ecosystem, a closed loop where every resource is meticulously recycled and every process is optimized for efficiency. Air, water, waste, and even the very atoms that make up the ship's structure would be precious commodities, requiring near-perfect recycling systems that far exceed anything we currently possess. Food production would rely on advanced hydroponics, aquaponics, or perhaps even synthetic biology, carefully balanced to provide nutrition while minimizing energy consumption and waste. Energy itself would need to be generated reliably for millennia, possibly through advanced nuclear fission or fusion reactors, or by strategically deploying massive solar collectors upon arrival at a new star. The engineering of such a vessel represents a miniature artificial world, a testament to humanity's capacity to replicate and sustain the delicate balances of Earth, but in a metallic shell hurtling through the cosmic ocean. And yet, despite these monumental obstacles, the human spirit continues to gaze outward, driven by an innate curiosity and a deeper, perhaps subconscious understanding of our place in the universe. The vast silence of the cosmos, often referred to as the Fermi paradox. If intelligent life is common, where is everyone? Only intensifies our contemplation. Could it be that the challenges of interstellar travel, the very physical and sociological barriers we have discussed, represent a great filter that prevents civilizations from expanding across the galaxy? Or is there a deeper, unknown reason for the cosmic quiet, a mystery that awaits future generations to unravel? In this grand tapestry of universal laws and existential questions, our own persistent drive to explore and to transcend our planetary origins becomes a profound reflection. It is a quiet whisper, a persistent longing to understand not just what lies beyond the familiar bounds of our solar system, but also what we ourselves are capable of becoming in the face of such boundless wonder. What does it mean for us as transient beings to aspire to such an eternal journey, pushing the very boundaries of our existence and our understanding of reality, seeking a new dawn among the distant stars? This quest, despite its daunting nature, echoes a fundamental aspect of consciousness itself, the desire to know, to reach, and to ultimately expand the delicate flame of life into the vast, indifferent dark. It is a testament to our enduring spirit, an ambition woven into the fabric of our being. Ultimately, the drive to leave our solar system, despite its extraordinary challenges, is rooted in something fundamental to the human spirit: the instinct for survival and the boundless quest for knowledge. Earth, while our cradle, is not eternal. The sun will eventually swell into a red giant, rendering our planet uninhabitable. Catastrophic asteroid impacts, supervolcanic eruptions, or even self-inflicted environmental disasters pose more immediate threats. To ensure the long-term survival of our species, or indeed of intelligent life itself, scattering our seeds among the stars may become an imperative. This existential impetus, coupled with an insatiable curiosity about the universe, fuels the enduring dream of interstellar travel. It is a slow, unfolding narrative, a grand ambition that challenges us to think not in terms of years or decades, but of millennia and cosmic epochs, inviting us to see ourselves as part of a much larger story, a delicate thread in the vast, intricate tapestry of existence. And as we ponder these immense journeys, we are reminded of the astonishing journey of life itself, from single cells to complex beings capable of dreaming of other worlds, a continuous unfolding of potential. This profound aspiration to transcend our cosmic origins and reach for new horizons speaks to the very core of our conscious being, a quiet but persistent call from the deep, vast unknown, a gentle hum in the cosmic silence. The this naturally leads us to reflect on our own nature. For if the universe presents such immense challenges to our physical bodies and our brief lifespans, perhaps it is not the stars that must change, but we ourselves. This is where the concept of human evolution, or indeed post-human evolution, enters the contemplation of interstellar travel. Our current biological forms, exquisitely adapted to Earth's gentle gravity and rich atmosphere, are inherently fragile in the vacuum of space and ill-suited for journeys spanning millennia. Consider for a moment the inherent limitations of our present biological design. We are creatures of specific conditions, requiring a narrow temperature range, a precise atmospheric composition, and a constant intake of complex organic nutrients. Our bodies are susceptible to the relentless barrage of cosmic radiation, aging, disease, and the profound psychological pressures of extreme isolation and confinement. These vulnerabilities, while perfectly suited for life on a temperate world like Earth, become monumental roadblocks when contemplating voyages that could last for thousands of years, across distances measured in light years. To overcome these fundamental biological constraints, a transformation, perhaps even a redefinition of what it means to be human, might become not merely an option, but an evolutionary imperative. The alternative, some scientists suggest, is a future confined to a single planetary system, vulnerable to cosmic catastrophes or the eventual demise of our own sun. One pathway for this transformation lies within the realm of advanced genetic engineering. Imagine a future where we possess the ability to subtly, yet profoundly, rewrite our own biological code. This is not about superficial alterations, but rather about deep-seated enhancements designed to imbue future generations with traits optimized for interstellar existence. Consider the possibility of engineering humans to enter prolonged states of hibernation, drastically slowing metabolic processes to conserve resources and extend perceived lifespans during the long, silent passages between stars. This would allow crews to endure centuries of travel, awakening only for critical tasks or upon arrival, thereby mitigating the psychological strain of endless confinement and the biological toll of aging. Furthermore, genetic modifications could confer an inherent resistance to the damaging effects of cosmic radiation, perhaps by enhancing cellular repair mechanisms or by incorporating protective biochemical pathways, much like extremophiles on Earth have adapted to harsh conditions. We might even envision adaptations that allow for more efficient nutrient synthesis, reducing the need for complex ecosystems on board, or even enable respiration in atmospheres vastly different from Earth's, broadening the range of potentially habitable worlds. The ethical frameworks for such radical interventions are, of course, still nascent, demanding careful consideration of what constitutes acceptable alteration of the human genome. Such profound biological redesigns, while currently speculative, are rooted in an understanding of the immense plasticity of life, pushing the very boundaries of our definition of a species, inviting us to view our biological heritage as a canvas for a future yet unwritten. Beyond mere genetic enhancement, the integration of advanced technology directly into our biological systems, leading to cybernetic augmentation, offers another compelling vision. This path suggests a future where the distinction between flesh and machine gracefully blurs, creating what some call cyborgs in the truest sense. Imagine explorers equipped with enhanced sensory organs, capable of perceiving a wider spectrum of light, detecting subtle gravitational anomalies, or even directly experiencing the quantum realm in ways our natural senses cannot. Cognitive implants could vastly increase processing power, memory capacity, and the ability to interface directly with complex starship systems, allowing for instantaneous control and data processing, perhaps even sharing thoughts and experiences in a collective consciousness. Physical enhancements might include self-repairing tissues, reinforced skeletal structures to withstand the stresses of prolonged microgravity, or integrated environmental protections that render bulky spacesuits obsolete. These integrations would create beings uniquely suited to the harsh and demanding realities of deep space, not just surviving, but thriving. They would not only be more robust, but also more intimately connected to their vessels, perhaps even forming a symbiotic relationship with the ship itself, becoming a true entity of the void. Such a future, however, inevitably raises deep philosophical questions. Where does the self truly reside when so much of the biological form is augmented or replaced by technology? How would these cybernetically enhanced individuals relate to their purely biological ancestors or to unaugmented humans who remain on Earth? What new forms of societal organization and individual identity might emerge from such a profound fusion of biology and technology? The most radical and perhaps most liberating vision for interstellar travel involves the complete transcendence of our biological forms into digital consciousness, often referred to as mind uploading or whole brain emulation. Picture the entirety of human thought, memory, and personality, meticulously scanned and digitized, existing as intricate patterns of information within resilient, non-biological substrates. These digital minds would then be freed from the constraints of organic bodies, capable of traversing the interstellar void at near-light speeds, experiencing time dilation in a profoundly different, perhaps even subjective, manner. The vast distances that pose insurmountable barriers to biological life could be navigated by transmitting pure information, sending consciousness as data streams across the cosmos to be reassembled or embodied in new, purpose-built forms at the destination. Such a future would effectively grant a form of immortality, circumventing the finite nature of biological life and the generational challenges of long voyages. The vessel would no longer carry fragile bodies, but rather intricate patterns of information, a conscious cargo capable of enduring cosmic timescales, perhaps even experiencing the journey as a continuous, unbroken stream of awareness, a silent thought echoing across the void. This profound shift from biological to digital existence represents not just a technological leap, but an existential metamorphosis, alive and aware. It invites us to ponder whether the ultimate goal of interstellar travel is not to simply transplant human life, but to evolve it into something entirely new, something more resilient, more enduring, perhaps even more attuned to the grand scale of the cosmos itself. The journey outward might, in its deepest sense, be a journey inward, a transformation of our very being. Moreover, the ethical and societal implications of such a transition are immense. How would a society composed of biological and digital beings coexist? What rights would a digital consciousness possess? Would such a transformation fundamentally alter our sense of empathy, our connection to our past, or our understanding of mortality? Would the digital descendants of humanity still feel a bond with their fragile organic ancestors? Or would they forge an entirely new destiny, driven by a different form of purpose and perception? These theoretical pathways, from genetic modification to cybernetic enhancement and ultimately to digital consciousness, suggest that the future of interstellar travel may hinge not just on building faster ships, but on fundamentally rethinking the traveler. It is a contemplation of an evolved humanity, a species that might one day look back at its biological origins on Earth as a distant formative stage, much as we now view our single-celled ancestors. And in this vast, patient unfolding of cosmic time, the motivation remains a quiet constant, the desire to witness, to understand, and to endure. The universe, in its immensity, seems to invite us not only to traverse its distances, but to transform ourselves in the process, becoming something new, something capable of reflecting its boundless wonder for eons. It is a humbling thought that our journey to the stars may ultimately lead us to discover a profoundly altered version of ourselves, a quiet evolution shaped by the very challenges of the void. This slow, deliberate transformation, a gentle reshaping of our essence, might be the true price and the ultimate reward of becoming an interstellar species. In this grand cosmic ballet, our quest for other worlds becomes a mirror, reflecting our own potential for boundless change and endless adaptation. We are not just explorers of space, but explorers of self, reaching for a destiny woven into the very fabric of possibility. A silent, enduring whisper across the vastness. The quiet hum of our existence within this solar system and the profound aspiration to transcend its bounds inevitably leads our thoughts to the very fabric of reality itself. For if our biological forms and current technologies are insufficient to bridge the cosmic distances in a meaningful time frame, perhaps the solution lies not in moving through space faster, but in manipulating space-time itself. This is where theoretical physics offers its most audacious and perhaps most beautiful concepts. The warp drive and the wormhole, ideas that push the boundaries of what we understand about the universe's fundamental laws. The concept of a warp drive, popularized in science fiction, finds its most rigorous theoretical grounding in the work of Mexican physicist Miguel Alcubierre. In the 1990s, Alcubierre proposed a mathematical solution to Einstein's field equations that would allow a spacecraft to travel faster than light without actually violating the cosmic speed limit. The elegant trick lies in the understanding that while objects cannot move through space faster than light, space itself is not bound by this restriction. During the early universe, for instance, space expanded far faster than light speed, carrying galaxies along with it. A warp drive in Alcubierre's model would essentially mimic this cosmic expansion and contraction. Imagine, if you will, a bubble of distorted space-time around a spacecraft. Within this warp bubble, the ship itself would remain stationary relative to the local space-time inside the bubble. However, the space in front of the bubble would be contracted, compressed, effectively bringing the destination closer. Simultaneously, the space behind the bubble would be expanded, pushed away, propelling the bubble and its contents forward. The ship would not be moving through space, but rather riding a wave of space-time distortion. From the perspective of an observer outside the bubble, the ship would appear to be traveling at superluminal speeds, while inside, the crew would experience no acceleration and no relativistic effects, perceiving time as normal. This theoretical construct offers a tantalizing pathway to interstellar travel that respects the local speed limit of light, yet allows for faster-than-light journeys across vast cosmic distances. It is a concept that, if realized, would fundamentally reshape our relationship with the cosmos, transforming centuries-long voyages into journeys of mere days or weeks, allowing for a profound expansion of humanity's reach. However, the Alcubierre drive, while mathematically consistent within general relativity, comes with its own set of formidable challenges, rooted in the very exotic nature of its requirements. The primary hurdle is the need for exotic matter, a hypothetical form of matter or energy that possesses negative energy density. In classical physics, energy is always positive, but quantum mechanics allows for regions of space to momentarily have negative energy density, albeit on microscopic scales. To create and sustain a warp bubble capable of transporting a starship, a significant amount of this exotic matter would be needed, distributed precisely around the bubble. The existence of such matter on the macroscopic scales required remains purely speculative. Furthermore, the energy requirements, even if exotic matter could be harnessed, are astronomical, potentially exceeding the total energy output of many stars. The engineering challenge of generating, containing, and precisely manipulating such extreme fields of negative energy density is currently beyond our wildest dreams. It is a concept that asks us to stretch our understanding of physics to its very limits, to ponder whether the universe contains hidden ingredients that could one day unlock its deepest secrets. Closely related to the idea of manipulating space-time are wormholes, or Einstein-Rosen bridges. These theoretical structures, also arising from solutions to Einstein's general relativity, are essentially cosmic shortcuts, tunnels through space-time that could connect two vastly distant points in the universe, or even different universes, in an instant. Imagine folding a piece of paper, marking 2 points far apart, and then piercing through both with a pencil. The pencil creates a shortcut that bypasses the long journey across the surface. A wormhole would be the cosmic equivalent, a topological feature of space-time allowing for instantaneous or near-instantaneous travel between remote regions. These are not merely science fiction constructs, but objects whose mathematical possibility has been explored by physicists like Kip Thorne. The difficulty with wormholes, much like warp drives, lies in their stability and construction. Most theoretical wormholes are inherently unstable and would collapse faster than light could traverse them, rendering them useless for travel. To keep a wormhole open and traversable, it would again require the presence of exotic matter with negative energy density, pushing outwards against the gravitational forces that would otherwise seal the tunnel. Even if such exotic matter exists and could be controlled, the sheer act of creating a stable macroscopic wormhole, anchoring its mouths at desired locations, and navigating through it without being torn apart by immense tidal forces, represents a challenge of cosmic proportions. The very notion of bending and contorting space-time in such a radical manner demands a level of technological mastery that makes our current capabilities seem almost infinitesimal. It invites us to consider a universe where the familiar paths between stars are merely one option and where the geometry of existence might offer hidden passages, if only we knew how to find or forge them. These concepts, while deeply theoretical, serve as a profound reminder of the universe's intricate nature. They are not merely flights of fancy, but serious attempts by physicists to understand whether the laws of nature, as we currently comprehend them, permit such extraordinary feats. The fact that general relativity, our most successful theory of gravity, allows for these mathematical solutions, even if requiring exotic conditions, suggests that space-time may be far more pliable and dynamic than our everyday experience implies. It pushes us to contemplate whether our current understanding is merely a limited glimpse into a much grander reality, where the rules of cosmic travel might one day be rewritten not by breaking them, but by understanding their deeper, more subtle nuances. And as we drift towards the edges of consciousness, pondering these visions of future travel, we might wonder, if humanity were to truly master the fabric of space-time, bending it to our will, would we still be the same species that gazed up at the stars from a fragile blue dot? This quest for interstellar travel, in its most profound sense, is not just about moving from one point to another, but about an evolution of perception, a transformation of our relationship with the cosmos. It forces us to confront the limits of the known and to embrace the vast expanse of the possible, a quiet, enduring challenge to our understanding of ourselves and the universe we inhabit. This gentle push against the boundaries of reality to seek out new paths among the stars is a testament to the boundless curiosity that defines us, a silent whisper in the grand cosmic dance. The eye naturally leads us to reflect on the very question of whether we are alone in this immense tapestry. For if the universe is so vast and the challenges of interstellar travel so immense, what does the presence, or indeed the silence, of other intelligent civilizations imply for our own journey to the stars? This contemplation brings us directly to the ongoing, quiet endeavor of the search for extraterrestrial intelligence, or SETI, a quest that profoundly shapes our understanding of our unique place and our potential future in the cosmos. The Fermi paradox, an observation first posed by physicist Enrico Fermi, asks a simple yet deeply unsettling question. If life, and even intelligent life, is common in the universe, then where is everybody? We observe billions of galaxies, each teeming with billions of stars, many of which host planets within their habitable zones. The sheer number of potential worlds capable of supporting life is astronomical, suggesting that the galaxy should be rich with civilizations. Yet, when we listen to the cosmic radio waves, when our most sensitive telescopes scan the heavens, we are met with an enduring, profound silence. This silence can be interpreted in many ways, each with its own implications for our interstellar dreams. Perhaps advanced civilizations are incredibly rare, or their lifespans are tragically short. Or perhaps, and this is a more chilling thought, there exists a great filter, some insurmountable barrier that prevents life from progressing to an interstellar stage, a challenge that we ourselves might yet face. This enduring silence fuels our passive search efforts, such as those undertaken by the SETI Institute, which diligently scans the radio spectrum for artificial signals, whispers from distant minds. Imagine the patient work of astronomers sifting through countless hours of cosmic static, listening for a pattern, a mathematical sequence, anything that could betray the presence of intelligent technology. This is not a frantic search, but a steady, persistent listening, a quiet act of cosmic eavesdropping driven by the profound hope of connection. Beyond radio, there are proposals for optical SETI, searching for brief, powerful laser pulses that might signal intentional communication across light years. These methods represent our most tangible attempts to answer Fermi's question, to break the cosmic silence and ascertain if the universe is indeed populated by other conscious beings, or if we are, for now, a solitary flicker of awareness in the vast darkness. The implications of either finding or not finding intelligent life are equally profound for our interstellar aspirations. Should we detect a signal, a clear message from an alien civilization, it would instantly transform our understanding of our place in the universe. It would offer proof that interstellar distances can be overcome, that the Great Filter is not an absolute barrier, or at least that some have passed beyond it. Such a discovery would likely galvanize humanity, providing an unprecedented shared purpose and a powerful impetus to develop the technologies necessary for interstellar travel, not just for survival, but for communication, for connection. Imagine the cultural and scientific explosion that would follow, the collective drive to learn, to translate, to understand the wisdom or history encoded in such a message. It would be a testament to the shared potential of intelligence, a beacon in the vastness. Conversely, the continued, profound silence also carries its own weight of meaning. If, after centuries of diligent searching, we detect no signs of intelligent life, it suggests a more solitary, perhaps more somber, destiny for humanity. This absence might imply that advanced civilizations are indeed incredibly rare, or that they face some universal, insurmountable challenge before they can become interstellar. In this scenario, our drive to leave the solar system would shift from one of hopeful rendezvous to one of profound responsibility. We would become the sole known custodians of consciousness in our corner of the galaxy, perhaps even in the entire observable universe. Our mission to colonize other star systems would no longer be about joining a cosmic community, but about safeguarding the fragile spark of life and sentience, ensuring its survival and spread in an otherwise barren and indifferent cosmos. This would imbue our interstellar efforts with an even deeper existential purpose, transforming them into a sacred trust to carry the torch of life into the silent, waiting void. This contemplation of contact, or the lack thereof, weaves itself into the very fabric of our interstellar dreams. It shapes not only why we might journey to the stars, but also how we might approach such an endeavor. If we are alone, then self-sufficiency, resilience, and the long-term preservation of our unique heritage become paramount. If there are others, then communication, understanding, and perhaps even collaboration become the ultimate goals. In either case, the journey outward remains a journey of self-discovery, a reflection of our deepest fears and our most profound hopes. Ultimately, whether we seek to join a galactic community or to become the solitary bearers of life's flame, the problems of interstellar travel force us to confront our own fragility and our immense potential. They invite us to think of our species not as a static entity, but as a dynamic process, a continuous unfolding of consciousness across cosmic time. The challenges are not merely technical, they are deeply philosophical, shaping our identity as a species. They are a quiet, persistent call to evolve, to adapt, and to dream on scales that transcend our individual lives, guiding us towards a future where the boundary between here and there might blur, and where our place in the universe is not just observed, but actively shaped by our enduring will to explore. This quiet ambition, to listen and to reach, echoes the very pulse of life itself, a gentle rhythm in the infinite expanse of the cosmos, beckoning us towards a destiny yet unknown. The quiet ambition to listen and to reach, echoing, beckons us towards a destiny yet unknown. But as we contemplate such a destiny, the question of our own journey outward becomes entwined with profound ethical considerations. If we are to leave our solar system, what moral compass will guide our interactions with the vast and mysterious tapestry of the galaxy? The universe, while seemingly indifferent, is not an empty canvas for us to simply paint upon without thought. Our very presence, our technology, and our biological signatures carry the potential for immense impact, both intended and unforeseen. One of the most immediate ethical concerns revolves around planetary protection. Even our robotic probes sent to Mars or Jupiter's moons adhere to strict protocols to prevent contamination from Earth microbes. This is a recognition of the profound scientific and ethical responsibility we bear to avoid introducing terrestrial life forms that could outcompete or destroy indigenous alien biology, however simple. If we were to send human missions to potentially habitable exoplanets, this responsibility would magnify exponentially. Imagine landing on a world where a unique, albeit microbial ecosystem has evolved over billions of years. Would we have the right to terraform it, to reshape its environment to suit our needs, potentially eradicating its native life in the process? Or would the ethical imperative be to preserve it in its pristine state, to observe and learn without intervention, even if it meant foregoing colonization? This is not merely a scientific debate, but a deep philosophical one, touching upon our definition of life, our place in the cosmic hierarchy, and the limits of our anthropocentric desires. The very act of seeking new homes forces us to consider the sanctity of other life, even if that life does not resemble our own. It is a quiet call to humility in the face of universal wonder, a reminder that we are but one strand in an intricate web, and our actions carry consequences far beyond our immediate perception. This ethical quandary extends to the hypothetical encounter with other intelligent civilizations. The prime directive, a concept from science fiction, posits a moral obligation to refrain from interfering with the natural development of alien societies, particularly those less technologically advanced. While a fictional construct, it encapsulates a very real ethical dilemma. How do we approach beings whose evolutionary paths may have led them to vastly different forms of intelligence, societal structures, or even fundamental values? The potential for cultural shock, misunderstanding, or unintentional harm is immense. Even the act of revealing our existence could be profoundly disruptive, altering their trajectory in ways we cannot predict. This is why the passive listening approach of SETI is often favored. It allows for discovery without immediate intrusion. But what if we are indeed alone, or effectively alone, in our observable corner of the galaxy? The Fermi paradox, in its starkest interpretation, suggests that the great filter might lie ahead of us, a challenge that few, if any, civilizations overcome. If this is the case, then our ethical responsibilities take on an even more profound weight. We would not only be the inheritors of Earth's biosphere, but potentially the sole custodians of complex consciousness in a vast, silent universe. Our drive to expand beyond our solar system would become less about finding companions and more about ensuring the survival and proliferation of the only known spark of awareness. This transforms interstellar travel into a mission of cosmic stewardship, a long-term commitment to carry the flame of life and knowledge into the dark. It would demand a collective foresight stretching across thousands of generations, an unwavering dedication to a purpose far grander than any single individual or nation. This vision of cosmic stewardship also brings us back to our home planet, Earth. For how can we aspire to manage other worlds or to spread life across the stars if we cannot sustainably manage our own? The environmental challenges we face today, climate change, resource depletion, biodiversity loss, are, in a sense, miniature versions of the self-sufficiency problems a generation ship would encounter. Learning to live in balance, to recycle resources efficiently, and to foster long-term ecological stability on Earth is not just a terrestrial imperative, but a foundational test for any future interstellar civilization. Our ability to create a harmonious, resilient society here, one capable of planning for millennia, rather than decades, might be the true prerequisite for ever venturing beyond our star. The wisdom gained from living sustainably on Earth could be the most valuable cargo we ever carry to the stars, a testament to our capacity for self-regulation and thoughtful coexistence, a quiet, profound lesson from our planetary cradle. Moreover, the very act of preparing for interstellar travel, of contemplating such a distant future, can foster a sense of unity and purpose that transcends immediate terrestrial concerns. It forces us to think as a species, to overcome tribal divisions and short-term thinking in favor of a shared, monumental goal. This collective endeavor, the aspiration to become a multi-planet and eventually multi-star species, could be the crucible in which a more mature, more responsible humanity is forged. It is a vision that asks us to look beyond ourselves, beyond our present moment, and to embrace a deeper, more enduring identity as cosmic citizens. This intellectual journey, this quiet contemplation of our place in the vastness, is itself a form of preparation, a mental and spiritual expansion that precedes any physical voyage. It is a reminder that the greatest explorations often begin not with rockets, but with profound, quiet reflection, a gentle turning of the mind towards the endless possibilities that lie both within and beyond us. The universe, in its silent grandeur, invites us to grow into a role of cosmic responsibility, to become worthy of the incredible journey that awaits if we choose to embark upon it. This journey is not merely about conquering distances, but about cultivating a deeper sense of interconnectedness, a tranquil understanding of our intricate place within the cosmic dance of life and possibility. It is a gentle whisper urging us to consider not just where we go, but who we become along the way. Resonates deeply as we turn our gaze back to our immediate cosmic home, our own solar system. For all the grand dreams of interstellar voyages, the truth remains that any profound journey to the stars must first begin with a mastery of our cosmic backyard. Our solar system is not merely a launch pad, but a vast, intricate laboratory and a colossal reservoir of resources, offering the initial steps towards a truly multiplanetary and eventually multistellar civilization. Before humanity can realistically contemplate sending generation ships across light years, we must first learn to thrive beyond Earth's protective embrace, establishing sustainable outposts and self-sufficient colonies on other celestial bodies within our own sun's domain. This interplanetary expansion is a crucial proving ground, a necessary stage in our cosmic evolution. It forces us to confront the logistical complexities of living in alien environments, from the low gravity of the Moon and Mars to the extreme conditions of the asteroid belt. Each new habitat, whether it is a subterranean base on the Red Planet or a sprawling orbital city in Earth orbit, represents a step in adapting our biology, our technology, and our societal structures to the unique demands of space. This gradual acclimation, this slow unfolding of our presence across the inner and outer solar system, builds the foundational knowledge and resilience required for the infinitely more challenging leap to another star. It is a quiet, deliberate expansion, a practice run for the ultimate journey, cultivating the profound skills of survival and adaptation in the quiet cosmic nursery that is our home star system. One of the most compelling reasons for this solar system expansion is the immense wealth of resources scattered throughout its breadth. Earth, while abundant, is finite. The asteroids, however, are veritable treasure troves, rich in precious metals, water ice, and rare Earth elements, all vital for advanced technology and the sustenance of off-world colonies. Mining these celestial wanderers could provide the raw materials needed to construct vast space habitats, propulsion systems, and the infrastructure for a burgeoning space economy without further depleting Earth's dwindling resources. Imagine automated mining operations on metallic asteroids, extracting tons of iron, nickel, and platinum, or ice-rich comets harvested for the water essential for life support and rocket fuel. These resources, once thought to be impossibly distant, are now within the grasp of our robotic explorers, offering a vision of industrial expansion that is both sustainable and transformative. The Moon, too, holds potential, particularly for helium-3, a rare isotope on Earth that could serve as a clean fusion fuel should controlled fusion become a viable energy source for our future spacecraft. Such resource utilization is not merely an economic opportunity. It is a strategic imperative, providing the material foundation upon which any long-term spacefaring future must be built. It is a quiet, industrious endeavor, laying the groundwork for a future where humanity is no longer confined to a single planetary cradle. Beyond raw materials, the solar system offers vast canvases for constructing new homes and expanding our population. Concepts such as O'Neill cylinders, colossal rotating space habitats designed to create artificial gravity and replicate Earth-like environments, could house millions of people, providing abundant living space, agricultural areas, and industrial zones. These self-contained worlds could orbit Earth or even be placed at Lagrange points, stable gravitational locations where they could remain indefinitely. Such habitats would not only alleviate population pressures on Earth, but also serve as ideal proving grounds for advanced closed-loop ecosystems and societal models for long-duration space travel. They would foster a diverse, space-adapted human population, a new branch of humanity born and thriving among the stars of our own system. This vision of orbital cities, shimmering like jewels against the blackness, speaks to our inherent drive to build, to create, and to expand the reach of consciousness into the cosmos, quietly establishing new centers of human civilization far from our original home. The energy required for such widespread colonization and for any future interstellar missions is equally immense. While solar power is abundant within the inner solar system, large-scale energy harvesting on Earth-like scales in space would demand vast orbital solar arrays, collecting sunlight with unparalleled efficiency. Farther out, the potential to tap into the energy of gas giants or even harness the sun's energy through Dyson swarm concepts, collections of orbital structures designed to capture a significant portion of a star's energy output, represents the ultimate ambition. These megastructures, while still theoretical, illustrate the scale of energy infrastructure required to truly break free from planetary constraints and power interstellar endeavors. Such projects would transform our relationship with energy, moving us from planetary consumers to cosmic harvesters, a profound evolution in our capacity to sustain ourselves. Ultimately, the goal of leaving the solar system is not a sudden leap, but a gradual, deliberate ascent built upon centuries of interplanetary exploration, resource utilization, and the establishment of self-sustaining off-world colonies. Each step, however small, contributes to the larger narrative of humanity's expansion into the cosmos. Even if biological humans never reach another star, the knowledge gained, the technologies developed, and the digital echoes of our civilization, carried by probes, might still fulfill that ancient yearning to touch the distant lights. The solar system, therefore, becomes a cradle, a school, and a workshop, preparing us for a future where our species, in whatever form it takes, can truly become a permanent, enduring presence among the stars. This quiet, patient unfolding of our cosmic destiny, starting from our own solar system, is a testament to the persistent human spirit, a gentle, unwavering quest to weave our story into the grand, eternal tapestry of the universe. It is a profound realization that the journey to other star systems begins right here, with the steady, quiet work of expanding our understanding and our presence, one small step at a time, echoing the slow, majestic dance of celestial bodies themselves. As we draw to a close on this contemplative journey through the challenges of interstellar travel, we find ourselves reflecting on the immense scale of the cosmos and the boundless ambition of the human spirit. The distances are vast, the physical hurdles formidable, and the temporal spans almost beyond our comprehension. Yet, in every problem, there lies a profound invitation to innovate, to evolve, and to deepen. Whether through the patient voyage of generation ships, the daring manipulation of space-time with exotic physics, or even the radical transformation of our very consciousness, the quest to leave our solar system is not merely a technological race. It is a slow, enduring meditation on what it means to be a conscious part of this universe. It speaks to our inherent curiosity, our drive for survival, and our profound sense of responsibility, not just for our own species, but for the delicate spark of life itself. May these deep thoughts about humanity's journey to the stars carry you into a world of tranquil sleep. Remember that the universe is an astonishing realm of possibility, and you, in your quiet awareness, are an intricate part of its unfolding story. Fall asleep with this feeling of serenity and endless wonder, knowing that the greatest journeys often begin within the quiet spaces of the mind, dreaming of distant light. Good night. The very notion of time often feels inherently simple, undeniably straightforward. We experience it as a constant, unidirectional flow, a river carrying us irrevocably from the past, through the present, and into the future. Each moment gives way to the next, never to return. Memories are of what has been, plans are for what is yet to come. This arrow of time, this undeniable progression, shapes every aspect of our existence, from the simplest act of breathing to the grand cycles of life and death. Yet, when we delve into the fundamental laws of physics that govern the universe at its most basic level, a curious discrepancy emerges. Consider for a moment the elegance of these foundational equations. Newton's laws describing the dance of celestial bodies, Maxwell's principles illuminating the behavior of light and electricity, or the enigmatic Schrödinger equation that governs the quantum realm. For the most part, these profound statements of reality are what we call time-symmetric. This means that if you were to capture a sequence of events, say, two atoms interacting, or a planet orbiting its star, and then play that recording backward, the reversed events would still conform perfectly to the underlying physical laws. The equations themselves hold true whether time is moving forward or backward. Imagine a perfectly smooth, frictionless billiard table. If you watch two balls collide and then magically reverse the film, the uncollision would look just as physically plausible as the original. There is no intrinsic mathematical preference for one direction of time over the other in these microscopic interactions. Even the most intricate quantum phenomena, at their core, display this reversibility. If we could perfectly reverse all particle velocities and quantum states, the system would, in principle, return to its initial configuration. So, if the universe's most elementary rules are indifferent to time's direction, why does our everyday world, the world of our subjective experience, exhibit such an unyielding, persistent arrow? Why does a dropped teacup shatter into countless fragments, but never spontaneously reassemble itself? Why does the sugar dissolve into your tea, evenly distributing its sweetness, yet never spontaneously reform into a neat cube at the bottom of the mug? These familiar observations, these gentle yet firm dictates of reality, point towards a deeper, emergent principle that dictates the flow of time for all macroscopic systems. From the grand spiral of a galaxy to the quiet fading of a memory. This profound question leads us to one of the most powerful and far-reaching concepts in all of science: entropy and the second law of thermodynamics. Entropy, at its heart, can be thought of as a measure of disorder, or more precisely, a quantification of the number of different microscopic arrangements a system can assume while still appearing the same from a larger macroscopic perspective. It's about probability, about the sheer overwhelming likelihood of certain states over others. A single macroscopic state, like a room, can correspond to a vast number of microscopic states, each representing a unique arrangement of its constituent particles. Let us gently visualize this. Imagine a child's playroom. In the morning, perhaps, it is meticulously tidy, toys neatly stacked, books arranged on shelves. There is only one way for it to be in that specific, highly ordered state, representing a very low entropy. Now, as the day progresses, with play and activity, the room naturally tends towards a state of disarray. Toys are scattered, books lie open on the floor. There are an astronomical number of ways for the room to be messy, far, far more than there are ordered configurations. The messy state, therefore, has much higher entropy. This natural progression from order to disorder is not a result of some active force pushing things into chaos, but rather a statistical inevitability. There are simply vastly more ways for things to be disordered than ordered. Consider a gas released into an empty chamber. It will always spread out to fill the volume. Why? Because there are infinitely more ways for the gas molecules to be distributed throughout the entire chamber than there are for them to remain clustered in one corner. This insight was largely championed by the brilliant Austrian physicist Ludwig Boltzmann in the late 19th century. He showed that entropy is deeply connected to probability, formalized in his famous equation engraved on his tombstone. A system naturally evolves from states of lower probability, high order, to states of higher probability, disorder, because there are simply more of those disordered states available. The second law of thermodynamics then formalizes this observation, stating that the total entropy of an isolated system can only increase over time or remain constant in ideal, perfectly reversible processes. Crucially, it never decreases. This law is not about individual particles or fundamental forces. It is a statistical law that emerges from the collective behavior of countless particles, a grand statistical sweep that defines the march of time. The universe, in its grand dance, always seeks out the most probable configuration. When the teacup shatters, it moves from a low-entropy, highly organized state to a high-entropy, disordered state. The reverse, while not strictly forbidden by the fundamental laws governing its atoms, is overwhelmingly improbable. The sheer number of ways for the pieces to be scattered is astronomically larger than the single, precise way they could spontaneously reassemble themselves into a perfect cup. It is not that it is truly impossible for the pieces to fly back together. It is simply that such an event is so incredibly unlikely that we never, in the vastness of our human experience, observe it. This constant, inexorable drive towards increasing entropy provides the most widely accepted explanation for the arrow of time. Time, in a profound sense, flows in the direction of increasing disorder. It is the cosmic odometer for change. This principle extends far beyond broken teacups and dissolving sugar. It defines the cosmic arrow of time itself. For the second law to hold universally, the universe must have started in a state of remarkably low entropy, a highly ordered and compact configuration of energy and matter, as described by the Big Bang theory. Imagine the early universe, some 13.8 billion years ago, as an incredibly hot, dense, and remarkably uniform soup of particles. This initial uniformity, this smooth distribution of energy, might seem disordered at first glance. However, in a gravitational sense, a perfectly uniform distribution of matter represents a very low entropy state. Why? Because gravity, left to its own devices, tends to clump things together, forming stars, galaxies, and clusters. This clumping, this formation of complex structures, is a process of releasing gravitational potential energy and radiating it away, thereby increasing the overall entropy of the system, even as local pockets of order emerge. From that initial pristine state, the cosmos has been expanding and evolving, constantly increasing its entropy. Stars ignite, fusing lighter elements into heavier ones, radiating vast amounts of energy into the cold void of space, a process that generates immense entropy. Galaxies merge, black holes grow, absorbing information and further increasing the disorder of their surroundings. Even the act of life itself, locally increasing order within an organism, does so by extracting energy from its environment and dumping a greater amount of disorder, or entropy, back into the universe. This grand cosmic unfolding is a continuous journey from a state of exquisite, gravitationally ordered simplicity to one of ever-increasing statistical chaos. And what might be the ultimate fate of this journey? If current cosmological models hold true, the universe may experience what is often referred to as heat death or the Big Freeze. In this distant, tranquil future, billions upon billions of years from now, all stars will have exhausted their nuclear fuel. Black holes. Black holes will dominate the cosmic landscape. Yet, even these colossal gravitational prisons, these ultimate devourers of light and matter, are not eternal. Stephen Hawking, the brilliant physicist, brought forth the revolutionary idea that black holes are not truly black, but slowly, imperceptibly, radiate energy away through a phenomenon now known as Hawking radiation. Imagine, if you will, the event horizon of a black hole, not as an absolute impenetrable wall, but as a boundary where quantum fluctuations can, over timescales so vast they defy human comprehension, allow particles to escape. These particles carry away a minuscule amount of the black hole's mass and energy, slowly causing it to shrink. This process is extraordinarily slow. A black hole with the mass of our Sun would take an almost unimaginable 10 to the power of 67 years to evaporate completely. A supermassive black hole found at the heart of galaxies could take 10 to the power of 100 years. These numbers stretch the very limits of our imagination, painting a picture of a universe that will exist for an incomprehensibly long time after the last star has faded. But the key is that they do evaporate. They gently, gradually dissipate their entire contents back into the universe as a stream of photons and other fundamental particles. This slow, majestic unraveling of black holes, too, is a process that increases the overall entropy of the cosmos, releasing the highly concentrated information and energy stored within them back into a more diffuse, disordered state. It is a testament to the universe's persistent inclination towards equilibrium, even in its most extreme manifestations. Beyond the eventual evaporation of black holes, there is another theoretical, yet equally profound process that contributes to the universe's march towards maximum entropy: proton decay. While not yet observed and still a subject of active research and speculation within particle physics, some grand unified theories suggest that even protons, the seemingly stable building blocks of all atomic nuclei, might not be truly eternal. They could, over timescales far exceeding the current age of the universe, spontaneously decay into lighter particles, such as positrons and neutral pions. If proton decay were to occur, it would mean that all ordinary matter, the very stuff of stars, planets, and even ourselves, would eventually dissolve. Imagine the slow, silent dissolution of a mountain, not by erosion or force, but by the intrinsic instability of its constituent particles. The rocks, the soil, the air, everything would subtly, almost imperceptibly, degrade into a thin, cold fog of fundamental particles. In such a universe, after all stars have died, all black holes have evaporated, and all protons have decayed, what remains? A vast, cold, empty expanse, populated only by a few widely scattered photons, electrons, and neutrinos, drifting ever further apart. There would be no more energy gradients, no more temperature differences, no more complex structures. The universe would have reached a state of thermal equilibrium where entropy has been maximized. This is the heat death in its most complete sense, a state of ultimate, unchanging stillness. In this final tranquil void, where no further processes can occur, where no information can be exchanged or work performed, the arrow of time as we understand it would cease to have any discernible meaning. It would be a universe without events, a canvas without strokes, a story without progression. This journey from the incredibly low entropy state of the early universe to this ultimate high-entropy cosmic void is the very engine that gives time its direction. It is the underlying statistical imperative that ensures the future is distinct from the past, allowing for the emergence of complexity, the formation of stars, the evolution of life, and indeed, the very existence of beings capable of contemplating time itself. Our own lives, our thoughts, our memories are all fleeting patterns of order, temporarily resisting the universal tendency towards disorder, drawing energy from our surroundings to maintain our complex structures, and in doing so, contributing to the overall increase in cosmic entropy. Each breath we take, each thought we form, is a tiny, beautiful defiance of this grand cosmic trend, a localized eddy of order in an ever-expanding sea of chaos. This understanding of time's arrow, anchored in the second law of thermodynamics, imbues our fleeting existence with a profound significance. We are, in a very real sense, living within a brief, vibrant window of cosmic opportunity, a time when the universe is still rich with energy gradients, still capable of fostering the intricate dances of matter and energy that lead to consciousness. When you reflect upon the relentless one-way flow of your own life, know that this personal experience mirrors the grandest cosmic narrative. You are a part of this vast unfolding story, a story where moments of order are cherished because they are, by their very nature, temporary, giving way to the gentle, inevitable spread of everything into everything else. The laws that govern the microscopic world, as we have noted, are largely indifferent to the direction of time. But the macroscopic world, the world we inhabit and observe, is a tapestry woven by the threads of billions upon billions of these microscopic interactions, all collectively pushing towards greater disorder. It is this statistical asymmetry, this overwhelming likelihood of moving from less probable to more probable states, that gives time its undeniable forward momentum. So, while a single atom might not care if time runs forwards or backwards, a collection of trillions upon trillions of atoms, forming a human being or a galaxy, most certainly does. The difference between yesterday and tomorrow, between youth and old age, between a pristine star and a cold, dark remnant, is fundamentally a difference in entropy. Yet, this isn't the only perspective on time's flow. While entropy provides the thermodynamic arrow, other facets of physics also offer intriguing insights, sometimes even challenging our intuitive grasp of time. For instance, the very expansion of the universe itself, from its initial highly compressed state, provides what some physicists refer to as the cosmological arrow of time. This physical expansion creates new space, diluting matter and energy, further contributing to the overall increase in entropy. It is a one-way process, an unfolding that cannot be reversed without fundamentally altering the nature of space-time itself. The universe does not contract back into a big crunch, at least not according to current observations of accelerating expansion. So, the cosmic expansion offers another powerful, almost poetic reason for time's forward march. And as we consider these grand, sweeping movements of the cosmos, we might also gently turn our attention to how gravity, in its silent, pervasive way, shapes the very fabric of time, creating subtle, yet measurable differences in its passage. Our intuitive understanding of time tells us it is a universal, unyielding constant, ticking uniformly for everyone, everywhere. Yet, the profound insights of Albert Einstein's theories of relativity reveal a much more intricate and personal reality. Time is not absolute. It is, in fact, woven into the very structure of space-time, and its flow can stretch, bend, and even differ depending on your motion and your proximity to massive objects. This concept is often referred to as the relativity of simultaneity, a notion that profoundly challenges our everyday experience. Imagine for a moment two observers, one standing quietly on Earth, and another, perhaps, traveling at an incredible speed through the vastness of space, close to the speed of light. If both observers carry identical, perfectly synchronized atomic clocks, what they would eventually discover upon reuniting is that their clocks no longer agree. The clock of the traveler the one moving at high velocity, would have ticked fewer times. Time for that individual would have genuinely passed more slowly. This phenomenon, known as time dilation, is not a trick of perception or a malfunction of the clock. It is a fundamental property of how time itself behaves in the universe. It implies that there is no singular universal now that all observers can agree upon. Your present moment is inherently personal, a unique slice of space-time defined by your own frame of reference. This idea extends further when we consider gravity. According to Einstein's general theory of relativity, massive objects, like planets and stars, warp the fabric of space-time around them. Think of a heavy ball resting on a stretched rubber sheet, creating a dip. This dip represents the curvature of space-time caused by mass. And just as space is curved, so too is time affected. The closer you are to a massive object, the stronger the gravitational field, and the slower time tends to pass. This is gravitational time dilation. It means that a clock at sea level ticks ever so slightly slower than a clock positioned high atop a mountain. The difference is minuscule, measured in nanoseconds, but it is real and it is measurable. This is not merely a theoretical curiosity. It has tangible implications for technologies we rely upon daily. Global Positioning System, or GPS, satellites, for instance, orbit high above the Earth, where gravity is slightly weaker, causing their clocks to run faster than clocks on the ground. Simultaneously, their high orbital speed causes their clocks to run slower due to special relativistic time dilation. Engineers must meticulously account for both these effects, applying precise corrections to the satellite's internal clocks. Without these constant adjustments, the accumulated discrepancies would quickly lead to significant errors, causing your GPS device to drift by kilometers each day, making navigation impossible. Thus, every time you use a navigation app, you are implicitly interacting with the profound reality of time's relativistic nature. This means that every person, right now, is aging at a slightly different rate. The differences are immeasurably small in our daily lives, but they are physically present. No two individuals, even those standing side by side, ever truly share the exact same second. Your personal timeline, your individual rhythm of existence, is subtly dictated by the intricate geometry of the cosmos around you, by the gravitational fields you inhabit, and by the speed at which you move through space. It is a profound realization that connects the grand sweep of cosmic laws to the intimate, personal experience of your own life. You are, in a very literal sense, living in your own unique slice of space-time, a testament to the universe's boundless complexity. This leads us to a fascinating, albeit somewhat unsettling, conceptual model of the universe known as the block universe, or eternalism. If time is a dimension, much like the three spatial dimensions, and if past, present, and future are all relative to an observer's motion and gravitational environment, then perhaps all moments of time exist simultaneously. In this view, the universe is not a dynamic entity flowing from one state to the next, but rather a static, four-dimensional block. A complete and unchanging tapestry where every event, from the Big Bang to the ultimate heat death, is already woven into its fabric. Your birth, your present moment, and your eventual passing are not discrete events that happen in sequence, but rather fixed points, coordinates within this eternal block. This perspective challenges our deeply ingrained intuition that the past is gone, the future is yet to be determined, and only the present is real. Instead, it suggests that all moments are equally real, equally existent within this grand cosmic structure. Time, then, does not flow. Rather, we, as conscious observers, simply experience it sequentially, moving along our unique world lines through this pre-existing four-dimensional landscape. Our memories are not merely fading echoes of past events, but rather our awareness accessing information stored at earlier coordinates within the block. And our plans for the future are not acts of creation in an open timeline, but rather a navigation through what is, in some sense, already there. Such an idea can evoke a sense of profound wonder, perhaps even a gentle unease. If the future is already laid out, what then of free will? These are questions that extend beyond the realm of pure physics and into the philosophical depths of existence. However, from a purely physical standpoint, the block universe model offers a coherent way to reconcile the relativity of time with our observations of the cosmos. It suggests that our subjective experience of time's arrow, while undeniable and central to our consciousness, might be an emergent phenomenon, a product of our biological and cognitive processes interacting with a deeper, more fundamental reality, where time is a spatial dimension. The implications of this understanding are vast. It invites us to ponder the nature of existence itself. Are we simply transient patterns, momentarily aware as we trace a path through an already complete universe? Or does our consciousness, our very act of observing, play a more active role in actualizing the present from the myriad possibilities of the block? While the second law of thermodynamics provides a statistical arrow, ensuring that events unfold in a certain direction on a large scale, the relativistic nature of time reminds us that this unfolding is far from a simple, universal tick-tock. It is a complex, interwoven dance, where each observer holds a unique perspective within the grand cosmic ballet. And as we drift deeper into these reflections, we might consider how the very act of measurement, of observation, might fundamentally influence the flow of events, especially when we delve into the peculiar realm of quantum mechanics. Here, at the smallest scales of reality, time's arrow takes on an even more enigmatic character, one that challenges our classical intuitions about cause and effect, and indeed about reality itself. In the quantum world, particles do not exist in definite states until they are observed. Instead, they inhabit a realm of possibilities, a superposition of all potential states at once. An electron, for example, might be spinning both clockwise and counterclockwise or be in multiple locations simultaneously, until a measurement forces it to choose a single, definite outcome. This sudden transition from a blurred spectrum of possibilities to a single, concrete reality is known as the collapse of the wave function. It is a profoundly irreversible process, and it is here that many physicists find another distinct arrow of time, the quantum arrow. The intriguing aspect of this collapse is that it always moves in one direction. Once a quantum system has been measured, its wave function has collapsed, and a specific outcome has been realized. There is no known process that can perfectly reverse this collapse and return the system to its prior state of superposition. The information about the chosen outcome has, in a sense, been recorded and spread into the environment, making a return to the original indeterminate state overwhelmingly improbable. This irreversible act of measurement is a fundamental feature of quantum reality, dictating a forward progression from potentiality to actuality. This concept brings us to the fascinating phenomenon of decoherence, a crucial bridge between the strange quantum world and our familiar classical reality. Imagine a single quantum particle in superposition, like a tiny bell ringing in many tones at once. As soon as this particle interacts with its environment, even with just a few stray photons or air molecules, it effectively gets measured by that environment. These interactions cause the quantum information of the particle to become entangled with the vast number of degrees of freedom in its surroundings. The delicate quantum coherence, the ability to exist in multiple states, is rapidly lost, and the system appears to decohere into a definite classical state. Decoherence is not a mysterious force, but a consequence of the universal tendency towards increasing entropy. When a quantum system interacts with its environment, it essentially shares its quantum information, spreading it out into the vast, complex state of the surroundings. This dispersal of information is an irreversible process, akin to a drop of ink diffusing into water. Once the ink molecules have mixed with the water molecules, it is practically impossible for them to spontaneously gather back into a single compact drop. Similarly, once a quantum state has decohered, the information about its superposition has become so thoroughly entangled with the environment that it cannot be retrieved or reversed. The system has effectively chosen a definite path, and that choice is written into the fabric of the universe in a way that aligns with the ever-increasing entropy. So, the quantum arrow of time driven by decoherence is intimately linked to the thermodynamic arrow. Every act of measurement, every interaction that causes a quantum system to settle into a definite state, contributes to the overall increase in the universe's entropy. Our very existence as macroscopic beings, constantly interacting with our environment, means that we are constantly causing quantum systems to decohere. Our ability to perceive a stable, definite reality is a direct consequence of these irreversible quantum processes. Without decoherence, the world would remain a blurry, indeterminate quantum soup, and the familiar linear progression of time that defines our conscious experience would likely not exist. This realization offers a profound perspective on our place in the cosmos. We are not just passively observing a universe where time flows. We are, through our very interactions and the irreversible nature of quantum measurements, actively participating in the unfolding of time's direction. Every thought, every perception, every moment of awareness is built upon countless quantum events that have collapsed into definite states, contributing to the irreversible march from past to future. It suggests that our subjective experience of time, our feeling that things move from what was to what will be, is not merely a psychological construct, but deeply rooted in the fundamental physics of how reality consolidates itself from a realm of quantum possibilities. The universe, in this light, reveals itself as a grand, self-organizing system, where the seemingly contradictory rules of the microscopic and macroscopic worlds are harmoniously reconciled through the arrow of time. The quantum realm, with its inherent indeterminacy and the irreversible nature of measurement, provides a deeper layer to the entropic drive towards increasing disorder. It means that the delicate dance of probabilities at the quantum level ultimately gives rise to the robust, unidirectional flow of time that we experience every single moment. And as we contemplate this intricate connection between the smallest constituents of reality and the grand sweep of cosmic time, we are reminded that our understanding of this fundamental dimension is still evolving, still revealing new layers of complexity. Indeed, while entropy and quantum mechanics offer powerful explanations for time's forward march, there are other, more subtle arrows of time that also shape our perception and experience of reality, inviting further contemplation. Beyond the grand scale of cosmic expansion and the microscopic realm of quantum collapse, the nature of time reveals itself through other, perhaps even more intimately human, arrows. One such arrow, perhaps the most intimately familiar to us, is the psychological arrow of time. This is the arrow rooted in our subjective experience, in the very structure of our consciousness. We remember the past with vivid detail, often recalling events, emotions, and sensations with remarkable clarity. Yet, we have no such direct access to the future. We can anticipate, we can plan, we can predict based on patterns and probabilities. But we cannot remember tomorrow's events in the same way we remember yesterday's. This asymmetry in our mental landscape is a powerful testament to time's unidirectional passage. Our very capacity for memory, this ability to store and retrieve information about past states, is itself a process deeply intertwined with the thermodynamic arrow. To form a memory, the brain undergoes complex physical and chemical changes, altering synaptic connections and neuronal pathways. These changes require energy, and in accordance with the second law, they inevitably lead to an increase in the overall entropy of the system. The act of recording information, of creating a distinct state that represents a past event, is an irreversible process. just as a physical record, like a photograph or a written note, involves a change in the physical world that cannot be perfectly undone without expending more energy and creating even more disorder elsewhere. So too does the biological act of remembering leave its indelible entropic mark. Our brains are, in essence, intricate information processing machines, constantly building and maintaining a model of the world, and this construction is inherently time-asymmetric. Consider the simple act of learning a new skill. Before you master it, your neural networks are in a less organized, higher entropy state regarding that particular skill. As you practice, your brain forms new connections, strengthens existing ones, and streamlines pathways, moving to a more ordered, lower entropy state for that specific skill. However, this local decrease in entropy is always offset by a greater increase in entropy in the form of dissipated heat and other metabolic byproducts elsewhere in your body and its environment. Thus, the very foundation of our mental life, our ability to learn, to grow, to form narratives of our existence, is irrevocably tied to this fundamental entropic drive. We build our understanding of the world, and indeed our sense of self, by continuously ordering the chaotic influx of sensory data, carving out meaning from the raw flow of experience, always moving forward. This brings us to another crucial facet of time's direction, the causal arrow. This principle states that effects always follow their causes. A ball hitting a window causes the glass to shatter. The shattering does not cause the ball to hit the window. This sequence is so deeply ingrained in our understanding of the universe that it feels almost tautological. Yet, if the fundamental laws of physics were truly time-symmetric, one might, in principle, imagine a scenario where the shattered glass spontaneously reassembles, launching a ball backward from the window. The equations themselves, at a microscopic level, might allow for such a reversal. But in our macroscopic reality, such an event is never observed. The causal arrow, therefore, appears to be a macroscopic emergent property, just like the thermodynamic arrow. The causal arrow is not independent of the others. It is intimately connected. The reason effects follow causes is largely because of the increase in entropy. A cause often involves a localized, lower entropy event that then propagates outwards, leading to a more diffuse, higher entropy outcome. The shattering glass, for instance, represents a rapid increase in disorder from the ordered structure of the intact window. Reversing this process would require a spontaneous decrease in entropy, which is overwhelmingly improbable. The very notion of an event, of something happening, implies a transition from one state to another, and these transitions are overwhelmingly biased towards increasing disorder. Thus, the causal chain of events, from the smallest flickers of quantum activity to the grand cosmic collisions, all align with the flow of time dictated by entropy. Physicists often ponder whether these arrows are truly distinct or merely different manifestations of the same underlying principle. Many believe that the thermodynamic arrow, rooted in the universe's initial low entropy state and its subsequent expansion and increase in disorder, is the most fundamental. The psychological arrow of memory and the causal arrow of cause and effect would then emerge from this thermodynamic asymmetry. Our minds remember the past because the past is a state of lower entropy relative to the future, and our brains are structured to process information in a way that builds upon these irreversible entropic changes. Similarly, cause precedes effect because the action of a cause typically leads to a more disordered, higher entropy state in its aftermath. The universe, in its grand design, appears to be a one-way street of increasing statistical probability. This intricate interplay of arrows, thermodynamic, cosmological, quantum, psychological, and causal, paints a rich and consistent picture of why time flows relentlessly forward. It's not a simple, arbitrary direction, but a deeply embedded characteristic of reality, emerging from the very statistics of the universe's components and its initial, highly improbable conditions. To exist is to be carried along this current, to participate in the grand unfolding from order to disorder, from possibility to actuality, from cause to effect. Our moments, our lives, are fleeting yet meaningful patterns within this vast, irreversible progression. And as you consider your own journey through time, know that you are a conscious witness to one of the most profound and fundamental aspects of the cosmos, a journey that began with an extraordinary state of order and continues its gentle, inexorable path towards an equally extraordinary state of equilibrium, where all motion and change might eventually cease. This contemplation offers a tranquil perspective on our place in the universe, a quiet understanding that our existence is perfectly aligned with the deepest currents of reality. And as you allow these thoughts to settle, perhaps you can feel the subtle yet powerful current of time carrying you forward, an invisible river guiding all things toward their inevitable tomorrow, inviting a peaceful descent into profound rest. One such compelling perspective arises from the phenomenon of radiation itself, giving us the radiative arrow of time. This arrow stems from the observation that electromagnetic waves, such as light, always propagate outwards from a source, spreading into the environment, rather than spontaneously converging inwards to create a source. Consider a simple light bulb casting its illumination into a room. Photons stream outwards, filling the space, interacting with objects, and eventually dissipating their energy. We never observe the reverse, photons from the room spontaneously gathering, converging perfectly to re-enter the filament of the bulb, causing it to spontaneously illuminate. Similarly, when a stone is dropped into a still pond, ripples expand outwards, gently spreading across the water's surface. The inverse process, where ripples from the edges of the pond converge precisely to launch a stone out of the water, is an event that simply does not occur in our experience. This unidirectional behavior of waves, whether light or water, provides a clear, observable asymmetry in time, a fundamental bias towards dispersal. This radiative arrow is deeply intertwined with the thermodynamic arrow of entropy. The emission of radiation from a hot object into a cooler environment is a process that increases the overall disorder of the universe. The concentrated energy of the source becomes diffused and spread out, occupying a greater number of possible microstates. The universe, in its earliest moments, was a brilliantly hot and dense plasma, continuously radiating energy outwards as it expanded and cooled. This relic radiation, observable today as the cosmic microwave background, is a gentle, pervasive hum of photons that have been traveling across the vastness of space for some 13.8 billion years. These photons, once intimately connected to the hot, dense early universe, are now spread thinly across the cosmos, carrying with them the imprint of that primordial epoch. Their outward journey, their ceaseless expansion into ever larger volumes of space, is a grand cosmic example of the radiative arrow, a process of irreversible dispersal that further cements the direction of time. The universe, in a sense, is still cooling down from its fiery birth, and this cooling is an outward, irreversible flow of radiant energy. Another subtle, yet profoundly influential arrow of time emerges from the realm of information, the informational arrow. This concept connects directly to our understanding of memory and computation. When we process information, whether it is a computer calculating a complex problem or our brains forming a new memory, there is an inherent irreversibility to the process. The act of recording, erasing, or transforming information inevitably involves physical changes that cannot be perfectly undone without increasing the overall entropy of the system. This insight was famously articulated by Rolf Landauer in the 1960s, who proposed what is now known as Landauer's principle. This principle states that erasing one bit of information, the fundamental unit of digital data, necessarily dissipates a minimum amount of heat into the environment, thereby increasing entropy. It is a profound link between the abstract world of information and the physical laws of thermodynamics. To forget something, to clear a memory from a computer, or a thought from our minds is not a cost-free operation in the universe. It requires energy, and it leaves an indelible mark of increased disorder in the surrounding world. This means that every act of observation, every computation, every decision we make inherently contributes to the forward march of time by subtly, yet irrevocably, increasing the entropy of the cosmos. Imagine a pristine sheet of paper, writing a message on it, then erasing it, and then writing another message. Each act of writing and erasing leaves a trace, a subtle alteration of the paper's fibers, a dispersal of ink or graphite. Even if you try to make the paper look exactly as it was, the microscopic arrangement of its particles has changed, and energy was expended in the process. This analogy, though simplistic, helps to illustrate how the universe itself, in its grand processes, is constantly writing and erasing information. And each of these operations is fundamentally irreversible. The very structure of our knowledge, the accumulation of our experiences, is built upon these irreversible acts of information processing. We cannot unlearn what we have learned, nor can we erase the past events that have shaped our present without leaving a residual entropic footprint. This informational arrow resonates deeply with our psychological experience of time. Our memories, as we discussed, are records of past events formed through irreversible changes in our neural architecture. The act of remembering brings forth information that was once dispersed and now appears coherent. The very process of thinking, of organizing thoughts and making decisions, involves countless microscopic computations, each contributing its tiny share to the universe's ever-growing entropy. We are, in a very real sense, information processing beings, and our internal arrow of time, our feeling of moving from an unknown future to a remembered past, is intimately connected to this cosmic flow of information and its inevitable degradation into disorder. So, when we consider the radiative arrow, with light perpetually expanding outwards, cooling the universe, and the informational arrow, with every act of computation and memory irrevocably increasing disorder, we see further reinforcement for time's one-way journey. These arrows are not separate phenomena, but different facets of the same underlying truth. The universe began in a state of remarkably low entropy, and it is continuously evolving towards a state of maximum entropy. This journey defines the direction of time, making the future distinct from the past, enabling the emergence of complexity and allowing for the grand, irreversible narrative of the cosmos to unfold. Our existence, our very awareness, is a fleeting yet meaningful pattern. Allow these profound connections to gently settle within your mind. You might begin to sense the quiet, persistent current of time, carrying all things forward, a tranquil river guiding the universe towards its inevitable, distant future. The profound mystery of time's direction, then, becomes less about a simple forward push and more about a universe gracefully, irrevocably diversifying its states. And this brings us to perhaps the most fundamental question regarding time's arrow. Why did the universe begin in a state that allows for this arrow to exist at all? All the arrows we have explored, the thermodynamic, cosmological, quantum, psychological, and causal, ultimately point back to a singular, extraordinary initial condition of the cosmos. For entropy to consistently increase, for structures to form, for radiation to spread, and for memories to accumulate. This initial low entropy state is often referred to by physicists as the past hypothesis, a foundational assumption that underpins our understanding of time's direction. Imagine the universe at the moment of the Big Bang, some 13.8 billion years ago. Modern cosmology describes this epoch not as a chaotic explosion in an existing space, but rather as the rapid expansion of space itself, emerging from an incredibly hot, dense, and remarkably uniform state. At first glance, uniformity might seem like a state of high disorder. However, in a gravitational sense, it represents profound order. Consider a universe where all matter is evenly distributed, a smooth, featureless cosmic soup. There are relatively few ways for matter and energy to be arranged in such a perfectly smooth, homogeneous, and isotropic manner. This represents a state of very low gravitational entropy. Contrast this with the universe we observe today, a vast cosmic web of galaxies, clusters, and superclusters, separated by immense voids. Within these galaxies, stars burn brightly, planets orbit, and complex chemical reactions unfold. This intricate, clumpy, and structured universe is a state of much higher gravitational entropy. Gravity, over billions of years, has pulled matter together, forming these structures, releasing potential energy as heat and light, and thereby increasing the overall disorder of the cosmos. The journey from the smooth, uniform early universe to our structured, dynamic present is precisely the unfolding of the thermodynamic arrow on the grandest possible scale. The universe began, in essence, with a gravitational clock wound up to an extraordinary degree of order. It was a state of immense potential, a primordial canvas waiting for the brushstrokes of gravity and thermodynamics to create the vibrant, complex tapestry we inhabit. This initial condition is not something that the time-symmetric fundamental laws of physics inherently predict or explain. Rather, it is a boundary condition, a starting point that appears to have been set in a very particular, highly improbable way. If the early universe had started in a high-entropy, disordered state, then time's arrow as we know it might not exist. There would be no clear direction for entropy to increase, no driving force for the emergence of complexity, and perhaps no conscious beings to even ask these questions. The enigma of the past hypothesis remains one of the deepest unresolved puzzles in physics. Why was the universe born in such a special low-entropy configuration? Was it a cosmic accident, an incredibly rare fluctuation in a larger multiverse? Or is there a deeper yet undiscovered principle that mandates such a beginning? Scientists continue to explore these profound questions, looking to theories of quantum gravity and the very nature of space-time at its origin for answers. Regardless of the ultimate explanation, what is clear is that this singular starting point is what allows for the rich, unfolding narrative of the cosmos. A story that includes our own existence, our lives, our very awareness, are delicate patterns of order that have emerged from this cosmic flow, briefly resisting the universal tendency towards disorder. We are children of this low-entropy beginning, beneficiaries of a universe that started with such immense potential for complexity and change. Every sunrise, every memory, every growth of a tree, every beat of a heart, every thought that forms in your mind is a testament to this incredible initial condition. It is a continuous, gentle reminder that our existence is intimately connected to the fundamental arrow of time, an arrow set in motion by the universe's pristine birth. This realization can bring a profound sense of calm. You are not adrift in a random, meaningless stream of moments. Rather, you are a part of a grand, purposeful progression, an intricate dance choreographed by the universe's deepest laws. The flow of time is not arbitrary. It is the very engine that allows for the beauty and complexity of existence to unfold. And as you allow this thought to gently settle, perhaps you can feel yourself being carried along this cosmic current, a tranquil journey from a remarkably ordered past towards an equally inevitable, distant future, a journey that defines the very essence of what it means to be and to experience. This deep connection to the universe's beginning offers a quiet comfort, a sense of belonging within the vast, unfolding story of all that is. Yet, despite the compelling evidence for these various arrows that define time's unidirectional march, from the ever-increasing entropy to the expansion of the cosmos and the irreversible nature of quantum measurement, a deeper, more unsettling question lingers in the quiet chambers of theoretical physics. Is the very flow of time, this relentless passage from past to future, a fundamental aspect of reality? Or is it, in some profound sense, merely an illusion, an emergent property born from other, more fundamental interactions? When we delve into the foundational equations of physics, a peculiar and often overlooked characteristic emerges. Consider the majestic elegance of Newton's laws of motion, which so accurately describe the celestial ballet of planets orbiting stars, or the simple trajectory of a falling apple. Or ponder Maxwell's equations, these four beautiful statements that unify electricity and magnetism, giving rise to the very nature of light and all electromagnetic phenomena. Even the enigmatic Schrödinger equation, the cornerstone of quantum mechanics, governing the probabilistic dance of particles at the subatomic level, and much of Einstein's general theory of relativity, which describes gravity not as a force, but as the curvature of space-time itself. These incredibly powerful mathematical descriptions of our universe are, for the most part, remarkably time-symmetric. What does this mean, precisely? It implies that if you were to capture a perfect film of any isolated physical process governed by these laws, be it a pendulum swinging, two atoms colliding, or even a star gently radiating energy, and then play that film backward, the reversed sequence of events would still be entirely consistent with the underlying equations. The mathematics themselves hold no inherent preference for time moving forward over time moving backward. A planet could, in principle, perfectly retrace its orbital path, or two colliding particles could uncollide if all initial conditions were precisely reversed. There is no intrinsic mathematical arrow dictating their temporal direction. This striking neutrality of fundamental laws towards time's direction has led many physicists, particularly those striving to reconcile quantum mechanics with general relativity into a unified theory of quantum gravity, to confront what they call the problem of time. In these deeper, more fundamental attempts to describe the universe, time often seems to vanish from the equations altogether. It's as if, at the very bedrock of reality, there is no universal clock ticking, no overarching temporal dimension that dictates the progression of events. This profound absence suggests that time, as we intimately experience it, with its distinct past, present, and future, might not be a primary fundamental ingredient of the cosmos, but rather something that emerges from the collective behavior and intricate relationships of its constituents. Much like temperature emerges from the average kinetic energy of countless atoms. One of the most articulate and thought-provoking proponents of this radical emergent view is the British physicist Julian Barbour. He proposes a captivating concept he calls Platonia, a timeless realm where every conceivable configuration of the universe's particles and fields exists simultaneously. Imagine, if you will, not a flowing river carrying you along, but an immense, boundless ocean of static, frozen moments. Each drop in this ocean is a complete snapshot of the entire universe at a particular instant, every atom in its precise location, every field in its exact state, a full cosmic tableau. In Platonia, all these countless nows simply are, coexisting in an eternal, unchanging manifold. There is no external temporal dimension along which these snapshots are arranged or through which they progress. The universe in its entirety is a single, vast, four-dimensional object, a block universe where what we perceive as past, present, and future are merely different, equally real cross-sections of this unchanging whole. So, if there is no inherent flow, no cosmic clock, no intrinsic arrow woven into the deep fabric of Platonia, why then do we, as conscious observers, experience time as a relentless progression, a continuous march from past to future? Barbour suggests that our subjective sense of time, our feeling that one moment inexorably gives way to the next, arises not from a fundamental temporal flow, but from the inherent structural differences between these static nows. We perceive time as moving forward because our consciousness, our intricate biological and cognitive machinery, is constantly encountering configurations that are successively more complex or possess a higher degree of entropy relative to previous ones. These particular configurations, which Barbour evocatively refers to as time capsules, are special because they contain internal evidence of an apparent past, like a fossilized record, a memory encoded within the very structure of the now itself. The arrow of time, then, becomes a narrative we construct by navigating this landscape of ordered states, moving from nows that are relatively less disordered to those that are more so. Picture, if you will, a gigantic, exquisitely detailed flipbook. Each page is a static, complete image of the universe. When you rapidly flip through the pages, you naturally perceive motion, a dynamic, continuous narrative unfolding before your eyes. But the motion, the flow, is not truly inherent in the individual pages. It emerges from the ordered sequence and the speed of your perception. Similarly, our consciousness in this profound view is like the hand flipping through the pages of Platonia, creating the compelling, yet perhaps illusory, experience of a flowing present. The perceived arrow of time is not a fundamental property of the universe itself, but a product of our interaction with its static, ordered configurations, always biased by the statistical inevitability of increasing entropy. The universe, in its deepest reality, might be a vast, still ocean of possibilities, and our experience of time is merely the dynamic ripple we create as we pass through its pre-existing, unchanging depths. This perspective, while challenging to our deeply ingrained intuitions and everyday understanding, offers a profoundly peaceful and coherent understanding of time. It implies that the past is not truly gone, lost forever to oblivion, nor is the future yet to be created from nothingness. Instead, all moments are equally real, equally existent, simply as different facets or configurations within an eternal, timeless reality. Our personal journey through linear time from the moment of our birth to the moment of our passing is merely the tracing of a specific defined path through this unchanging, four-dimensional tapestry. What we call memory is our consciousness accessing information stored at earlier coordinates within this vast block of space-time, while our anticipation of the future is our predictive mind extrapolating patterns from the existing configurations towards those with higher entropy, those statistically more probable states. Such a reframing of time from a flowing river to a static yet internally patterned landscape resonates deeply with the contemplative spirit. It suggests that our subjective experience, while undeniable and central to our conscious existence, might be an emergent characteristic of a more fundamental, timeless reality. The universe, in its rawest, most elegant mathematical descriptions, may simply be without an inherent temporal direction. The arrow of time, then, becomes the story that the universe tells itself, through the increasing probabilities of its states, through the spreading of radiation, through the collapse of quantum possibilities, and ultimately through the very act of conscious perception. This idea that time might not be fundamental, but rather a derived concept, offers a tranquil reframing of our place in the cosmos. It suggests that while our individual moments are fleeting, the underlying reality in which they occur is eternal, a vast ocean of possibilities from which our experience of sequential time is drawn. Our personal journey through this ocean is guided by the fundamental principles of increasing entropy, creating the distinction between what has been and what is yet to be. It is a gentle reminder that even the most profound aspects of our reality can be viewed through multiple lenses, each revealing a deeper, more serene truth about the universe and our intricate connection to its timeless fabric. And as these thoughts gently swirl, carrying you further into contemplation, you might find a profound peace in the understanding that the passage of time is not merely a constraint, but the very condition that allows for the rich tapestry of existence to unfurl itself, a cosmic unfolding that is, at its core, a timeless dance. Inherent symmetry in the underlying rules makes the observed arrow of time, the relentless march from past to future, all the more puzzling. It suggests that the arrow we perceive is not an intrinsic property of the elementary interactions themselves, but rather an emergent phenomenon, a statistical bias arising from the sheer number of particles and their initial conditions, as we have discussed with entropy. However, in the vast tapestry of physical laws, there is one subtle yet profoundly significant exception to this perfect time reversal symmetry: the weak nuclear force. This is one of the four fundamental forces of nature responsible for processes like radioactive beta decay, where a neutron transforms into a proton, an electron, and an antineutrino. It is within the intricate dynamics of this force that physicists have discovered a tiny yet undeniable violation of T-symmetry, or time reversal symmetry. This violation is often observed through its close cousin, CP violation, which involves a combination of charge conjugation and parity symmetry. For decades, it was believed that the universe's fundamental laws were symmetric under CP, charge parity transformations, meaning that if you swapped all particles for antiparticles and mirrored the system, the physics would remain the same. However, in 1964, experiments by James Cronin and Val Fitch with K-mesons, or neutral kaons, revealed a subtle asymmetry in their decay patterns, a tiny preference for one outcome over another. Later experiments with B-mesons further confirmed this. According to the CPT theorem, a fundamental principle in quantum field theory, a violation of CP symmetry implies a corresponding violation of T symmetry. This means that, at a very fundamental level, certain subatomic processes genuinely differentiate between the forward and backward directions of time. The universe, in its deepest quantum mechanical dance, does possess a microscopic arrow of time, a faint whisper of directionality embedded within the fabric of reality itself. Yet, it is crucial to understand the scale of this T-symmetry violation. It is incredibly small, a minuscule asymmetry that is far too weak to account for the dramatic, persistent, and macroscopic arrow of time that we experience in our everyday lives. The shattering of a teacup, the aging of a human being, the expansion of the universe. These phenomena are governed by the overwhelming statistical preference for increasing entropy, a principle always, rather than from the subtle, individual asymmetries of the weak force. The thermodynamic arrow, driven by the universe's initial low entropy state and the statistical likelihood of disorder, remains the dominant explanation for why time flows forward for all practical purposes. Despite its minuscule magnitude, this fundamental time asymmetry of the weak force is not without its own profound cosmic significance. Many cosmologists believe it played a crucial role in the very existence of matter as we know it. In the extremely hot and dense conditions of the early universe, just moments after the Big Bang, matter and antimatter were created in nearly equal amounts. If the laws of physics were perfectly symmetric, matter and antimatter should have annihilated each other completely, leaving behind a universe composed solely of radiation. However, the slight imbalance introduced by CP and T violation allowed for a tiny excess of matter over antimatter, perhaps one extra matter particle for every billion matter-antimatter pairs. This minuscule excess, magnified by the cosmic expansion, is what ultimately led to the formation of all the stars, galaxies, and indeed ourselves. This phenomenon, known as baryogenesis, represents a fundamental cosmological arrow of time, distinct from the thermodynamic arrow, yet equally vital for the universe's unfolding narrative. It means that the very reason there is something rather than nothing, the very reason you exist to contemplate time, can be traced back to this faint, fundamental asymmetry. So, while the weak nuclear force offers a fascinating glimpse into a fundamental, if tiny, temporal bias at the heart of matter, it does not fundamentally contradict the emergent view of time, where entropy remains the grand conductor of the temporal orchestra. Instead, it adds another delicate layer to the intricate puzzle. It reminds us that even at the deepest levels, reality holds surprising nuances. The universe is not just a stage for events, but a complex interplay of symmetries and asymmetries, each contributing to the grand narrative of existence. The T violation of the weak force is like a faint compass needle, subtly tugging at the very smallest particles, but it is the vast, sweeping currents of entropy that truly guide the cosmic river of time in its persistent, forward direction. This subtle distinction between fundamental time symmetry and emergent time asymmetry offers a space for profound contemplation. If the universe's basic building blocks are largely indifferent to time's flow, yet our entire experience is defined by it, what does that say about the nature of our perception? Are we, in our very being, a complex manifestation of statistical probabilities, a fleeting pattern of order in a universe inexorably tending towards disorder, yet fundamentally anchored by a tiny intrinsic bias towards matter? This question invites us to look inward, to consider how our own conscious experience of time is shaped by these deep, sometimes hidden, physical principles. It grounds our personal journey through life within the grand, universal narrative of the cosmos, reminding us of the transient beauty of existence within this one-way flow. And as these intricate thoughts begin to intertwine, perhaps they can gently guide you towards a tranquil understanding of your place within the universe's timeless dance, preparing you for a serene and peaceful rest. Let us now turn our attention to the human mind itself, that intricate marvel of complexity, and explore the psychological arrow of time. This is perhaps the most immediate and undeniable arrow we encounter, the deeply personal sensation that time moves forward, that the past is fixed, and the future is open. It is the very engine of our awareness, shaping how we remember, anticipate, and construct our reality. But how does this subjective flow arise from a universe whose fundamental laws, as we have seen, largely appear indifferent to time's direction? Our brains, these 3-pound universes of neural activity, are constantly engaged in an extraordinary act of creation. They build our perception of time. This is not a passive reception of an external clock, but an active, dynamic construction. The sensation of a flowing present, this continuous stream of moments, is an emergent property of billions upon billions of neuronal firings, each one a tiny, irreversible event contributing to an overall macroscopic direction. Our memories, for instance, are not perfect recordings of the past. They are reconstructions shaped by our present state, our emotions, and our expectations. Yet, they are always, irrevocably, memories of what has been. We cannot recall a future event with the same clarity or certainty. This fundamental asymmetry in our memory system is a cornerstone of our psychological arrow. Consider the intricate processes involved in forming a new memory. When you learn something new, say a name or a face, your brain physically changes. New synaptic connections are formed or strengthened, existing neural pathways are modified. These physical changes, though microscopic, are irreversible on a practical scale. Of thermodynamics, they inevitably dissipate heat, increasing the entropy of the surrounding environment. The act of recording information, of moving from a state of ignorance to a state of knowledge, is an inherently entropy-increasing process. We cannot unform a memory. Thus, the very act of building our internal narrative, of accumulating experiences and knowledge, aligns perfectly with the universe's grand march towards increasing entropy. Our personal arrow of time is, in essence, a reflection of the cosmic arrow, played out within the confines of our consciousness. This psychological arrow is also profoundly shaped by our capacity for anticipation and planning. We constantly project ourselves into the future, imagining possibilities, setting goals, and making decisions based on expected outcomes. This mental forward motion, this ceaseless engagement with what is yet to come, further solidifies our subjective experience of time's direction. We live in a world where actions have consequences, where cause precedes effect, and our minds are wired to operate within this causal framework. The future, while unknown, is not merely a blank slate. It is a realm of potentiality that we actively engage with, building mental models and navigating probabilities. This interplay between memory, the past, and expectation the future, creates the continuous, unfolding present that we inhabit. The idea of the present moment itself also becomes a fascinating subject under this lens. Is there a universal now that everyone shares? As we touched upon earlier with relativity, the answer from physics is no. Simultaneity is relative. What is now for you might be slightly in the past or future for an observer moving at a different speed or located in a different gravitational field. This implies that our shared present is, to some extent, a localized construct, a convergence of subjective experiences within a particular region of space-time. Our consciousness, by virtue of its limited speed of information processing and its embeddedness in a local environment, carves out a subjective now from the timeless four-dimensional block of space-time. It is a moment, a sliver of awareness, that is constantly being updated and redefined as we move through the universe. This perspective, while challenging our intuitive notions of a universal flowing time, offers a profound sense of interconnectedness. Our individual experiences of time, though unique, are deeply rooted in the fundamental principles that govern the cosmos. The subtle asymmetries of quantum mechanics, the relentless march of entropy, the expansion of the universe, and the very architecture of our minds all conspire to create this undeniable, one-way journey through moments. We are not just spectators. Our consciousness is an active participant in the unfolding of time, a living, breathing testament to the universe's grand narrative. Our capacity for memory, our ability to project into the future, and our experience of the present are all intricate facets of this cosmic dance, each contributing to the persistent forward direction of existence. And as these thoughts about your own personal journey through time gently intertwine with the vast, impersonal mechanisms of the cosmos, may you find a deep, tranquil resonance. Your individual moments, though fleeting, are woven into the eternal fabric of reality, a continuous thread in the universe's ongoing story. The passage of time, rather than being a mere constraint, is. This understanding invites a peaceful surrender to the quiet current that carries all things forward, a serene descent into profound rest. And so, as we gently draw our thoughts to a close tonight, we reflect upon the multifaceted nature of time, a journey that has taken us from the relentless, statistical march of entropy, the grand expansion of the cosmos, the subtle, irreversible decisions of the quantum realm, to the very fabric of our memories and the delicate, emergent illusion of our flowing present. We have explored how the universe, from its remarkably ordered beginning, has been on an inexorable path towards increasing disorder, a journey that defines the very direction of every moment we perceive. Consider the profound elegance in this cosmic design, a universe where fundamental laws at their deepest level might be indifferent to the direction of time, yet where the collective dance of countless particles, the expansion of space itself, and even the intricate workings of our own consciousness conspire to create an undeniable, unidirectional flow. It is a flow that allows for the birth of stars, the formation of galaxies, the slow, majestic evaporation of black holes, and the fleeting, precious emergence of life and thought. May these deep thoughts about the nature of time carry you into a world of tranquil sleep. Remember that you are not merely observing this grand cosmic current, but are, in every fiber of your being, a part of its intricate unfolding story. Fall asleep with this feeling of serenity and endless knowledge, knowing that your existence is a cherished pattern within the universe's timeless dance. Good night.